Am I audible?
Yes, Bhavna, you're audible.
Okay. Good afternoon, everyone. I'm Bhavna Kulkundi. Here again to welcome you all guys for the third day of Q-Basics workshop, which is organized by Q-Tangled in the collaboration of SW RGIT. So the further session will be taken over by Freya.
Yes, I'll just share my screen. Can you guys see the screen?
Yes, we can see.
Yes, Freya, it's visible.
Hi everyone, I'm Freya and welcome to the Python overview session. I hope you had a great time learning about maths and quantum mechanics from my friends Shivani and Lokesh. So today we'll get our hands dirty with coding. So this is meant to be an overview or revision of the basic concepts of Python. So the things that we'll be covering are, we'll see how to print statements, we'll see some of the data types of Python, we'll go through the if-else statement, while loop, for loop, functions, and we'll learn about how to import libraries. So let's head over to ripple.it, which is an integrated development environment, and it allows you to code in Python and test your output without having to install it. So to print a statement in Python, we'll basically just write print and use this curly brackets and then write whatever we want to print inside this code. So let's print hello world, and when I run it here, you will see on the output side that the hello world is printed over here. And so let's define a variable. So like a variable is a name given to a memory location. So we can define a variable by simply we can name it anything and then we can assign values to it. Like here I have made a variable named x and assigned a value phi to it. So now when I do print the variable named x, it will print here phi because that's what the value is stored inside that variable. So we can even perform mathematical functions in Python this way. So let's just define another variable named y and like assign a value 6 to it, and then we can perform mathematical functions like addition. So we'll just print x plus y, and when we print it, you will see that their sum is being printed here. We can even do subtraction, multiplication, division, and many more functions. So that was about the print statement. Now let's see the various data types in Python. So there are numeric types, sequence types, and mapping types. So in numeric types, we have integers, float, complex. And so integers is denoted by int in Python. And then we have sequence types, data types like list, tuple, range, and we also have mapping type like dictionaries, which is denoted by dict. So let's just see some practical examples so we can understand better. So to define a list, we can like name the variable anything. So here I'll just name it my list, and then we can so this square brackets denotes a list. So what I've done here is I've created a list which is basically stored in a variable named my list. Now inside that list, I can add anything. I can add numbers, I can add strings, I can even add more list inside it like this. So basically we can add anything inside the list, and to print it, we can just do print and then type my list, which is the name of our list. And as you can see, the list is printed over here. And to to like print the individual element of the list, we'll have to type in the index. So indexing in Python is done this way. So the first element is assigned the index of 0. The next element is assigned the index of 1, and so on. So like if in this list I want to print the first element of the list, then basically I'll do print, I'll write my list, and then I'll add the index 0 because that's what the index is of the first element. And when I do print, it will just print out the first element of the list. So same way I can print any element that I want from the list, and this is how it's done. So next, you can also change the characters of the list. Like if I want to change the second character of my list from 2 to 3, then I can do something like this. I can assign it the value of 3. And then now when I print my list, the value will be changed. See, from here it was 2 and now it has been changed to 3. So list is mutable, and because we can change the characters inside the list. Now let's move on to tuples. So tuples are basically immutable list because we cannot change the elements inside of a tuple. So let's just define a variable named tuple, and tuples are denoted by this round brackets, and then we can add anything inside a tuple. And the same way we can print it the way we used to print list, but the only difference is that we cannot change the elements inside the tuple like we used to do in the list. So now let's move on to dictionaries. Dictionaries are an unordered collection of items, and it has a key and a value. So like let's just make a variable named mydict, and then it's denoted with this curly brackets, and the one here is called the key, and the apple that I wrote is called the value. So dictionaries are unordered collection of items. So the way we so the key, the one I told you, it's called the key. It cannot be a mutable data type. So by mutable, I mean something like list. So the key cannot be a list. The value can be anything you like, and we can access the values this way. So we'll do print, we'll type in the name of the dictionary, and then if I want apple, then I have to put in the key of the value. So like I want the value apple, then I'll put in the key corresponding to it, which is 1. And when I run it, I'll get apple. So this is how we go about with dictionaries. So the next thing is the if-else statement. So if-else statement is used when you want to run different code on different conditions. So let's just see how it's done. So let's define a variable named num and give it a value 2. So like I want to do something like this. So if the number is positive number, then I want my code to print positive, and if it's negative, then I want to print negative. So we can execute something like this using the if-else statement. Like I can write the condition like if num is greater than 0, then print positive. Else print negative. So we have already defined number as positive, and when we run this code, we'll get positive because our num variable was positive. Now if I change it to -1, you'll see that it will print negative. So And there is also one more condition in this if-else statement known as elif. So if what if the number is 0, then it's not positive or negative, right? So we can add one more condition, like if num is equal to 0. So this equal to a checks with the Python if the number's value is 0 or not, and then we can print 0. So this is the, so let's just see the implementation if the number is 0. I think so. Let's just move on with the while loop. So while loop is used to iterate over a block of code as long as the condition is true. So for example, let's say n is equal to 5. Then what if we we want to print 5 uh, till the n, till n is greater than 0. So if I do n while n is greater than 0, print 5. So what this loop will do, it will keep on checking the value of n and will keep on printing 5. But this loop will go on to be like an infinite loop, since the value of n is not getting changed and it will always remain 5 no matter what. So we can add something like n is equal to n minus 1. So what this does is that it checks the value of n and then it reduces its value by 1. So it will print 5 up till it is greater than 0, and once it is less than 0, it will stop the loop and the code will end. So as you can see, it printed 5 for whenever the n's value was greater than 0. So now let's just look at the next thing, which is the for loop. So for loop is used to iterate over a sequence or iterable objects like list, tuple, strings. So let's say we have a list named num and it has the following elements inside it. Now, if we want to sum all of this, take a sum of all the elements inside the list, so we can implement this using the for loop. So let's just define another variable named sum and assign 0 to it. So the syntax of for loop is something like this. So for I in num. So what this basically does is that it takes each element from num and then implements the code that will write below it. So sum is equal to sum plus I. Sorry, I. So what this will do is it will go over each element in this list. Like for example, the first element is 1. So it will take 1 and then it will add it with sum, which is defined as 0. So 0 plus 1 is 1, and now it will assign that value to sum. So now the new value of the variable sum is 1. Now it will move on to the next value in the list, which is 2, and now it will again add it to it. So basically we'll get the sum of all the elements inside the list using this code, and then later we can print the value of sum this way. So we got the value of sum of all the elements inside the list. So this is the basic syntax of for loop, and this is how it's implemented. So the next is function. So a function is a group of release statements that performs a specific task. For example, let's look at the same function, which is sum, and now let's try to put all of this code inside a function. So like in programming, we all need to perform certain tasks again and again, and we cannot write the code for it like every time we perform it. So one way to do is that we can make a function and name it and put all that code inside the function. And then whenever we want to run that code, we can just call that function and use it again and again whenever we want to. So let's say I want to create a function that sums all the like elements that are provided to it. So this way we can define a function and then I'll name the function as sum. So a function needs input. So let's just put in two variables which we will input, and then let's define another variable, and what the functionality of this function is to sum the elements provided, right? So we'll just do x plus y and then we will return z. Now this is how the function is defined. Now when we want to implement it, we simply have to call the function by its name and then input two variables inside it. Like I want the sum of 5 and 8. So I'll just input these two elements and I print this. So I'll get the sum of 5 and 8. See, we got the sum as 13. So this is how we can define functions and like use the certain code again and again whenever we want to inside our coding. So the next is importing libraries. So Python has a ton of standard modules readily available for use. So like it also has it consists of various functions that we can call and we can use in our code. So to do that, we have to import these libraries inside our code. For example, Python has a module named math. So to import that, we will just write import math, and now the module is imported. So to use that, let's just use one of its functionalities called log. So math module contains a function called log, which allows us to get log values of any number that we want. So let's just define a variable named result. And when we have imported a library, the way to use it that we'll put the name of the library and then we'll put a dot and then we'll write whatever function we're using. Like I'm using log and I'll use it to the base 2 and then I'll enter whatever number I want like this, and now I'll print it. So I got the log of 5 to the base 2. So this is how libraries are used. And one more way to use it is that we can do something like from math import star. The star denotes everything that is there inside the math. So this way we will no longer have to use this math dot, and we can just use log to the base 5 like this, and we'll still get the same result. So this is how you can import a particular function from a module and use it. So there are a ton of more libraries and you can check them out on Python's official site. One more library that is another important library that is used in quantum computing is called NumPy, and it is used to create matrices and arrays and things like that. And I'm sure my friends Shivani and Lokesh must have explain to you about how matrices are used in quantum computing. So we'll just see how this library works. So we'll first import NumPy, and we'll import it as NP, just a short form. It's like a name, given to it. And now every time we'll use NP instead of NumPy. Now let's, so we can make arrays using it. So let's just make a one-dimensional array, and I'll name the variable as ARR. And then to make the array, we simply have to do np dot array, and we'll put in a list. So what this basically does is that it creates a one-dimensional array, and you can print it out this way. See, as you can see in the output screen. We can also create a two-dimensional array using NumPy. So to do that, we'll have to add another set of square brackets, and we'll add another list here. And now when we run it, we'll see that a two-dimensional array is created here. And the same way, we can also create a three-dimensional array using NumPy, and we can use it in quantum computing. So that was all about basic overview of Python, and you can check out some of those resources to learn more about it. So now let's move on to just a second. Yeah, now let's just move on to coding with Qiskit. So just a second. So in this, we'll see what a quantum circuit is. We'll build a quantum circuit. We'll learn about some of the gates like X gate, Y gate, Z gate, Hadamard gate, C0 gate. We'll also create an entangled state, and we'll simulate it and then later run it on an actual quantum computer. I hope you're excited about this part. So what is Qiskit? So Qiskit is a software development kit for working with noisy intermediate scale quantum computers, which are basically the quantum computers that are available right now. And it is an open source software. So what that basically means is that its code is available for everyone to view, and then you can, if you see some issues in that code, you can report it on GitHub, and you can also contribute to it by adding new pieces of code or by introducing new functions through GitHub. So basically it's available to everyone. And it has 4 fundamental elements in it. So the first one is Terra, and it is called the Earth element, and it is also the foundation on which the rest of the Qiskit lies. So it's basically the base layer, and it provides interface between hardware and software. So the next is Air, and it is known as the Air element, and it helps us to understand the limits of classical processors by demonstrating to what extent they can mimic quantum computation. So like it includes 3 simulator backends, which are Chasm simulator, state vector simulator, and unitary simulator. And you'll be learning more about this in the next lecture from my friend Vishal. So the third one is Aqua, and it is known as the water element. and it helps us to build algorithms for quantum computers. So these algorithms can be used to build applications in fields like chemistry, optimization, finance, and AI. So, and the last one is Ignis and is known as the fire element, and it is dedicated to fighting noise and error, and to like mitigate the noise and error inside the quantum computers that is there right now. So Qiskit is basically written in Python, and it also compiles the circuit to run on different backends like various simulators or quantum computers. So now let's see what is a quantum circuit. So quantum circuit basically has three parts: input, quantum gate circuit, and then output. So in input, we have your quantum states, which are initialized in some way. So in this case, all our states start at ket 0. So the next, there are gates that we apply on our states. So quantum gates are used to perform operations on qubits. So when we apply a quantum gate to a qubit, we change it in some way. So this is similar to how our classical gates operate. Like when we apply classical logical gate, classical gates on bits, uh, which are used in classical computing, they modify bits. For instance, if we apply the classical NOT gate, then it outputs as 1 if 0 is inputted, and vice versa. Similarly, in quantum computing, there's also a gate called the poly X gate. So if you input ket 0 to a poly X gate, we would obtain ket 1 and vice versa. And we'll learn more about this gate in the upcoming slides. But this is there. We apply gates, and then we modify our qubits to the output that we want. And then once we have done that, we created a circuit, we measure it. So yeah, now let's start building our quantum circuit. So we'll build the quantum circuit in quantum lab. So I am sure my friend Lokesh must have introduced you to IBM Quantum Experience yesterday. So when you log in into your IBM Quantum Experience account, this is how your screen will look like. And to start coding with Qiskit, we'll go to the IBM Quantum Lab, and we'll just click on the Launch Lab button. So it will redirect you to this notebook, and we'll click on a new file button. So yeah, it takes a bit time to load. So you guys can also try coding along with me if you want, and if you just want to see if it's your choice. So the first thing that we'll do is we'll import Qiskit, which is a library for quantum computing, and we can run. So this is basically called a cell, and you can run this by clicking the cell run button here. And yeah, so while the cell is running, you'll see a little star thing in this bracket, but since it ran very fast, we weren't able to see it, but hopefully we'll see it in the next cell. So just to check what version of Qiskit was imported, you can use this. So as you can see the star here, that means it's running. And this doesn't mean anything for us right now, but you can just check if you're running the correct version. So here we're running Qiskit Terra 0.717.4, and yeah, it'll give you the versions that we are running. So we can start by creating a quantum circuit made up of 1 qubit. So a quantum circuit is a function, and like a function needs an input. So like let's just define a variable named QC, and then we'll write quantum circuit. So quantum circuit is a function in this Qiskit library, and we need an input. So right now we are creating a quantum circuit of 1 qubit. So we'll just input 1 here and we'll run it. So what this does is that it creates a circuit with 1 qubit in it. So to visualize our quantum circuit, we can do something like QC dot draw, and then we can do MPL. So like MPL is Matplotlib library, and it's basically a style which like makes the circuit more nice for us to see. So it's basically just a visualization tool. So here you can see our 1 qubit circuit. We have not added any gates or anything to it, so it's just like this. So now, so this is how we create a quantum circuit, and this is a 1 qubit circuit. So yeah, let's now see the poly X gate. So poly X gate is a symbol qubit rotation through pi radians around the x-axis. So this is how the poly X gate is denoted, and this is how it's represented in the matrix form. So this is how the poly X gate looks. So it is equivalent to the NOT gate in classical computing, where 0 is converted to 1 and 1 is converted to 0. So in poly X gate, if we initialize our circuit as get 0 and if we apply the poly X gate, you will see here in the truth table that we'll get 1. And if we have get 1 as the input and we apply the poly X gate, we'll get 0 as our output. So let's just apply the poly X gate to our circuit here. So to apply poly X gate, we just have to do dot X and denote the index of the qubit to which we want to apply our gate. And here we only have 1 qubit, so we'll just run it. And now we'll draw our circuit. So as you can see, the X gate is applied on our qubit. So now let's just see how what it does to our qubit using a block sphere. So to like see the visualization on a block sphere, we'll have to use state vector simulator. So you will learn more about this in the next lecture, as I said previously, but let's just define a variable called this, and then we'll get our simulator. So as I mentioned earlier, air is the element of Qiskit that operates with all the simulators. So we'll just use air, and then we'll get our backend, which is here we're going to use state vector simulator. So we'll do that. And then we'll define another variable named Q object, and then we'll assemble our circuit. So our circuit's name was QC as we defined earlier. And now we'll also define another variable named state, and we will use the simulator that we imported, and then we'll run it on the Q object, and then we'll get the result. So yeah, this is what we'll do. And now we'll visualize this using a block sphere. So we'll plot it on a block sphere. So this is how it is done. So now let's just run this. So I don't know what mistake I made here.
I guess in the import statement, a symbol was not added. You can add a symbol in the.
Vishal, can you help me out?
Yeah. I've put it in the chat. Try from Qiskit import assemble.
Yeah, sure. So yeah, as you can see, our qubit was initialized to get 0, and then once we applied the X gate, now our qubit isn't like converted to get 1. So like, can you see the red arrow is pointing towards get 1? So that is what the X gate does. So now let's see what poly Y gate does. So poly Y gate is a single qubit rotation through pi radians around the y-axis. So this is how it is represented in the matrix form, and this is how the gate looks like. So now let's just again implement our poly Y gate here. So to implement poly Y gate, we basically have to do just dot Y instead of X. And once we run this, we'll draw this, and we can see that the Y gate is implemented over here. And now let's just see its implementation in the form of the block sphere. So yeah, we can just run it again. And now we can see that the so like it is rotated pi radians around the y-axis. So now let's look at poly Z gate. So poly Z gate is a single qubit rotation through pi radians around z-axis. So this is how it's represented and in the matrix form, and this is how it looks like. So now let's just implement it again in our quantum lab. So here, instead of Y, we'll just make it Z, because that's how poly Z is implemented, and we'll draw our circuit as we do. And now when we like run this code for implementation on a block sphere, we will see that the poly gate will have no effect on 0, as it changes 1 to -1. Like if the qubit is ket 1, it will change it to minus ket 1, and it will leave 0 unchanged. And it like we won't be able to see its representation because it's not in 3D, but it does rotate it pi radians around the z axis. But like if you want to see like how poly z gate is implemented, let's just apply first an X gate, because because it will convert our qubit, which is initialized to get 0 to get 1, and then we'll apply poly Z gate to like see what it basically does to our qubit. So here we applied the poly X gate first, and then we applied the poly Z gate. And now let's just run this code to see what its implementation is on the block sphere. So yeah, this is how it looks like. We won't be able to see the minus sketch here because this is not the 3D representation, but yeah. So the next gate is the Hadamard gate. And the Hadamard gate is a single qubit operation. And all the gates that we saw before this are single qubit operation. And what I mean by single qubit is that we can perform, like put this gate on one qubit too. We don't necessarily need two qubits for it. So it creates an equal superposition state of two basis states. As you can see, if we apply H gate to like get 0, this is how the superposition will be created. And if we apply H gate to get 1, this is how it will be created. So basically what Hadamard gate does is that it like rotates the qubit 90 degree around the y-axis, and then it followed by a 180-degree rotation around the x-axis. So let's implement that gate in our quantum lab. So here we'll just remove this, and to implement the Hadamard gate, we'll basically do dot h, and then we'll put in our 0, which denotes on what qubit the gate will be implemented. And then when we run qc.draw, we'll see that the Hadamard gate is implemented. So this is how it looks like. And when we see its implementation on the block sphere, so this is what it does to the qubit. So now let's look at another gate. So the next gate is the C0 gate. Now C0 gate is a 2-qubit gate, so it will require 2 qubits to be implemented. So the first qubit is referred to as the control qubit, and the second qubit is referred to as the target qubit. So C0 gate is basically an if gate. So like if the control qubit is get 1, then it applies poly X gate to the target qubit, and if the control qubit is get 0, then it will leave the target qubit unchanged. So like as you can see in this truth table here, in the first example, the control qubit is get 0, and so like it leaves the target qubit unchanged, and the output is the same as the input. In the next case also, the control qubit is get 0, and hence C0 gate does not do anything to like this. So, and the third input is get 1. So like the control qubit is get 1. So now it will apply a poly X gate on the target qubit, which is get 0. And as we understood earlier, the poly X gate basically converts get 0 to get 1. So that's why our output here is get 1, 1. And in the next example also, the control qubit, so like the control qubit is get 1, so it basically applies a poly X gate on the target qubit, and hence our output is get 1, 0. So let's see our implementation here. So the control NOT gate is denoted like this, and to like implement the control NOT gate, we'll first like define a quantum register. So quantum register is basically a register, and it stores qubits inside it. So like let's just define a variable named QR, and then do quantum register. So what this does, I'll input 2 as we want 2 qubits inside our quantum circuit. And what this basically does is that it stores 2 qubits inside the variable named QR. Now we'll also have to measure our circuit, and for that, we'll also need a classical register. So we'll just define another variable, and we'll do classical register, and then we'll also give the input as 2, as we need 2 bits to measure it. And now we'll define our quantum circuit with another variable as QC, and we'll input our quantum register and our classical register both inside it. So this is how it's done, and we'll just run it. And now we'll add our control NOT gate. We will just have to run this import again. And now we'll add our control NOT gate. So to do that, we'll do the name of our circuit, which is qc.cx, and we'll basically so here we have to put two inputs, which is the control qubit and the target qubit. So here our control qubit will be the first qubit and our target qubit will be the second qubit. So we'll run this. I guess again we have to import from Qiskit. Let's also import classical register. So yeah, it's done. And now we'll draw our circuit. So as you can see, the CMOS gate is applied, and here the first qubit is our control qubit and the second qubit is our target qubit. And now let's just see the implementation over here. See, since our qubit were initialized to get 0, our output is get 0, 0 because nothing was done, because as I explained to you earlier, we need our control qubit as get 1, and then only the CNOT gate will apply the poly X gate on the target qubit. So now we'll move on to the entangled state. So the entangled state of two qubits can be made via a Hadamard gate on the control qubit followed by a CNOT gate. So like this generates an entangled two qubit state known as Bell state. So this is how it looks. So it has a 50% probability of being measured in state get 0, 0 and 50% being measured in the state get 1, 1. So why this happens is because when we apply the Hadamard gate to our first qubit, it basically puts it in a superposition, and then it has an equal probability of being get 0 and get 1. And then when we apply a CNOT gate to it, 50% of the time it will be get 0, 0, and another 50% of the time it will be get 1, 1. And it has 0% chance of being in the measured states in the get 0 and 1 or 1, 0. So like this combined states cannot be written as two separate qubit states, because like while we measure, so like although our qubits are in superposition, measuring one will tell us the state of the other and collapse its superposition. So like even if we separate these qubits light years away, measuring one collapses the superposition and appears to have an immediate effect on the other. So now let's just implement this entangled state in our quantum lab. So to implement this entangled state, we'll just add a Hadamard gate to our first qubit. So we can do this by QR and then 0. So when we run this and draw it, we can see that first we applied the Hadamard gate to our first qubit, and then we applied a CMOS gate. So now we have to measure this circuit. So let's just insert a cell here, and to measure, we will basically write qc.measure. So we'll write input as QR, which is the quantum register that we define, and CR, which is the classical register that we define. And now we'll again draw it to like see how it looks. So as you can see, we added in the measurements. So now we'll run this. So first we'll run it on a simulator. So what a simulator basically does is that it simulates quantum properties on a classical computer. So a simulator, like as I said, it simulates quantum properties on a classical computer. So once we are satisfied the results, we can send it to IBM to run it on a real quantum computer. So we have 3 simulators available, which are chasm simulator, state vector simulator, and unitary simulator, as I mentioned in the first slide. And you'll learn more about this in the next lecture. So here we'll be using the chasm simulator. So let's just do that. So I'll insert another cell below it, and I'll first get my simulator. So as I said, air is the element which is responsible for the simulation, like it contains all the simulators. So we'll get it from here, and next we will define a variable named result, and we'll execute it, and we'll input the name of our circuit, and we'll also give the backend that we want to use. So here we're using the chasm simulator, and as we defined it in the variable name simulator above, so we'll just equal this backend to simulator. And now, since we want the result, we'll do this, and we'll run. Again, we'll have to import execute. So yeah, now this cell is successfully run, and to see our results, we'll have to import another. We'll have to import the histogram, because that's how we'll see the results. So from Qiskit dot tools dot visualization, we'll import plot histogram. So this is what we'll use to visualize our result, and then we'll use the result variable that we defined above, and then we'll get the counts and put in the name of our circuit here. Sorry, I have spelled it wrong. So as you can see, we get 50% probability of get 00 and 50% probability of get 0.1. And the slight difference is due to the errors in quantum computing. But yeah, this is what we basically had in mind, what our result would look like, and this is what it looks like. So now, since we're satisfied with what our results look like, we can run it on an actual quantum computer. So we'll insert another cell, and to run it on a quantum computer, we'll first have to load our account. So it's done like this, and we'll just run the cell. Yeah, so our account is loaded, and now we'll define a variable named provider to get the provider from IBM Q. So we'll do something like this. and the name of the provider is IBM-Q. Next, we'll see what backends are available. So to do that, we can do something like this. So like when we run this, sorry, again, I made the typing error. So here we can see all the backends available, like these are the name of the quantum computers that are available, like IBM 16, Melbourne, Armor, and there are many. So we can use one of them. So here I'll be using IBM Santiago. So to do that, we'll again define a variable named qcomp, and like we'll just do provider.get backend, and then we'll just write the name of our backend, which is, again, I made this mistake. Yeah, so I'll just write the backend that I'm using. So here I'm using IBM Santiago, and I'll just run this.
I think that backend is down.
I'll just use another one. So yeah, this works. So now we'll define another variable named job, and now we'll execute our circuit. So we'll input in the name of the circuit, which is QC, and then we'll like the backend that we're using, which is we defined it here. So we'll just equal this backend to the variable that we named it. And now from Qiskit tools dot monitor, will import something called job monitor, which will basically monitor our job that we'll be sending to the quantum computer. So yeah, we'll just input it, the job that we defined here, and we'll run it. So yeah, we got the job status is being validated. So like these jobs are basically submitted to real devices, and since they are public devices, there is a queue. So hence we got that our job is queued and the number of the queue. So depending on how busy the quantum computers are, the job might take a few minutes. So till then we can just define our result that we'll get from the job. So as you can see, the queue is reducing. So shortly our job will be run, and we'll just define our result by the time it gets run. And yeah, we'll get ready with the histogram through which we'll see our results. And here I'll input the name of my circuit. So hopefully in 1 or 2 minutes, it will be run on the real quantum computer, and we'll get our results back. And then we can run this cell. So now, as you can see, our job is actively running. So once it will be run, the data will be sent back to our servers, and as you can see, the job has now successfully run. So now we can just run this cell where we have defined the result. And yeah, so here we have the result. So the difference between the job run on the simulator and quantum computer is that here on the real quantum computer, we can see a few results for ket 01 and ket 10. And like, but on a simulator, we only had results for ket 01 0 and get 1 1. So the reason why this happens is that the simulator simulates a perfect quantum device, whereas the real quantum computers are prone to small quantum errors. So these errors are like getting lower with advancements made every day, but like we still haven't reached the perfect, like we haven't still reached the stage of a perfect quantum computer. So like we'll have these errors for right now, but hopefully in the future we can reach that stage and minimize these errors as much as we can. So yeah, that's it for it. We like run our we, we run our entangled state on the quantum computer, and that's it for this session. So thank you guys, and if you have any questions you can write in the chat and I'll try to answer is like all of them. So yeah, thank you.
Thank you, Freya. So if you guys have any doubts, you can put it in the chat box. And the second session will be taken by Vishal. So he'll continue.
Yes, hello everyone. Give me 1 second, I'll set everything up. Okay. I hope my screen is visible now.
Yes, it's visible.
Give me 1 second. Okay. Something's wrong now. Maybe at that till that time you can post your questions in the chat and Freya can answer that. I'm having a bit trouble here. Give me 1 second. Okay, I think now we are up. So hello everyone. So sorry for the trouble. So let me just present the screen. So yes, hello everyone and welcome to the second session of Coding with Qiskit. So we have gone through the mathematical properties, then we have looked over the quantum mechanics part, which my friend Lokesh and Shivani has explained you. Then Freya has explained you about introduction to Python elements and also a brief introduction to Qiskit, right? So I'll be taking over the ball and continuing on with a few more advanced concepts, right? So let's look. Let's look at today's agenda. So what we're looking at today is we'll be continuing this basically in two parts, right? We'll be starting with the learning part. So we'll be learning about custom rotation gates. So right now you just looked at the poly X, Y, and Z gates, right? What if instead of going all the way pi, what if you want to go somewhere in the between, right? So that's where custom rotation gates will come in. I'll explain about that. Then control gates. So we looked at one of the control gates, one of the multi-qubit control gates, CX, which Freya had explained. What if you want to control other gates using that, right? So we'll be looking over control gates by applying multiple controls and also even different gates other than X in this section, right? Next thing is importing the composer to notebook. So you looked at the Qiskit composer in the IBM Quantum the walkthrough which location Shivani had taken through, right? What if you can import the same in the notebook and let the composer do all the work for you? Sounds interesting, right? So we'll look over that too. And then we'll have a small discussion on backends. So when you're making your circuits, when you're making your basically making your operations and you want to do something, you want to run it on something. So that's where you run it on backend. It's similar to what you do in your classical computers too. In your laptop, when you run a Python code, you need something to run it on, right? You need your processors. So like that, we have backends on that. Next, we'll be getting our hands dirty with a bit of coding projects. So here are demonstrations just to get you started with thinking about quantum computing, or even start with small mini projects on quantum computing, right? So these are not really complex or big stuff. So it's basically the first project is quantum rock paper scissors. So we are working with random number generators. I'll explain with you why random number generation is kind of important. And I kind of thought explaining it with the game would be really amazing. So that's our first mini project. And the next would be demonstrating one of the buzzwords you might be looking around all over the news, that is the quantum teleportation, right? So let's get on with it, shall we? So let's start with the learning part. So the first section, as I told you, was about custom rotation gate. Now, Freya had explained that we have a few basis gates. So poly X gate, Y gates, and Z gates, right? What if you do not want to have the operation of those specific gates? What if you do not want to go all the way around pi, right? What if you want to stop somewhere in the between? Let's say you noticed when Freya had demonstrated, it went from 0 to 1. What if you want to stop somewhere in the between? That's where custom rotation gates come in. So these are very, very important to make very complex circuits. So that's why we'll be explaining about what these gates are. So Rx gate, the first gate, and if you can see the matrix it represents here, basically represents your X gate. So this would mean that you are having rotations along the x-axis. I'll show this more clearly in the demonstration part, which will come up in a few moments. So just remember, the Rx gate will be moving along the x-axis, and the convention we are taking here is we are moving anti-clockwise. Okay, so these rotation gates can be made to simulate the poly gates too. So poly gate is basically a rotation x gate with the angle as pi. Okay, that's why it goes all the way around down from up from 0, right? So the next gate which we can look is, since we are talking about axes, is Ry gate. So Ry gate is basically a rotation along the y-axis. So if you know the y gate can be simulated as the x gate if we put the angle as pi. We can also simulate many other gates using combinations of these rotation gates. So for example, the hard-marked gate, which we noticed there, the gate which basically implements superposition, can be simulated using Ry and Rx gate. So what we do is basically we apply an Ry rotation by pi by 2, so it stops halfway, and then we apply an X gate rotation by pi. So that's how we get the hard-marked gate, right? The next one would be RZ gate. Again, I'll be showing I think this concept would be clearer when you see the visualization, right? I'll go over that again too. So that will be done. Next thing is basically the RZ gate. So RZ gate is kind of rotation along the Z axis. And it's kind of difficult to see when you have the initial state as 0, as Freya had mentioned, because you're basically spinning along the same axis, because the 0 is basically pointed along the x-axis in the block sphere, if you visualize it. So that's why it's kind of a bit difficult to see it. But as with the other gates, the poly Z gate is basically RZ gate with a rotation of pi. We also have um, different gates inside Z gate because of the way the matrix is formed. So we can have something called as a root Z gate. We can have root X gates too, and root Y gates too. But we have something called a root Z gate, which is just a rotation of pi by 2. And then we have a 4 times root gate that is called a T gate, which we will have a rotation of pi by 4. Then we have the Hadamard gate. So we can also, as we simulated the Hadamard gate using Y and X, we can simulate the Hadamard gate using Y and Z, right? So that's why it's kind of important that rotation gates are so customizable. They are so great that you can build basically any gates using this. That's why sometimes you need that granularity, right? So let's kind of demonstrate the same on the quantum experience. So Freya, I'm sorry. Okay, so Freya had explained you about the quantum experience. So this is the quantum experience, and location Shivani also had gone through this. So I'll be using the quantum lab. So I've opened the lab for you directly, and I have already imported a few statements. So we are using the basic statements that are there. We need a quantum circuit, we need a quantum register, we need execute to run things, and we are using the visualization part to basically have your histogram and plot city. Yeah, now what we'll do is we'll basically start initializing the circuit. I like to name my registers. So I'll start with the name. So QR is equal to quantum register. Let's have it as 1, right? Then let's name our circuit as the variable circuit. So circuit is equal to quantum circuit. And then let's pass in QR in it, right? So when we pass in QR, we are basically making the quantum circuit with QR. And now what we want to do is we want to apply these rotation gates. So the basic syntax is we first call in the circuit, and then we put a dot, and then we call in the gate which we want. So in this case, let's say I want to have an RX gate. Call in Rx, and then I pass in 2 parameters. So the first parameter we pass in is by what angle do I want to rotate. So I want to rotate by, let's say, pi by 2 degrees. Okay, so I do pi by 2, and then I pass in what qubit should I be applying it to. So I want to apply it to QR. Okay, so do not worry about this part now. I'll explain this in a bit detail later. So what we are basically doing is we are running the circuit on the backend, and then we are going to visualize how it looks. So when we run the circuit, so here we go. We have rotated by around pi by 2, right? So this is the x-axis. I hope you can see my mouse pointer. So this is the x-axis, and we are kind of rotating around this. So if I want to show you a bit more clearly, I'll change the angles and kind of run again. So you can see that we are kind of rotating it around. So if I were to increase, let's say, the angle to pi, it's going to go down now. It has moved completely down. So if I want to increase it by 3 pi by 2, it's going to go all the way like this. So it's moving like this right now. So we can have different rotations to any custom rotation. So we are having this now. And if you want to see how it looks on this circuit.draw, output is equal to npm. We're calling in the matplotlib. So this is how it goes. You will have an Rx with the angle which you're rotating it down below. So I've set it to pi by 8 now. That's why you're seeing pi by 8 here. I hope this is visible.
Yes,
Yes.
it's visible.
Okay, give me 1 second. The computer decides to hang for no reason. So please bear with me on that. Okay, so I guess we have, yeah, so we have applied the Rx gate. Now let me apply the Ry gate. I want a different, let's say, angle with this. So the Ry gate moves along this axis. So the Y axis. So I'll show you with different angles. It will help you visualize. So when we are moving along, we are moving along the Y axis, right? So this is the plane which we are moving around. So if we are to do complete pi, it goes back to 1, right? And the same thing, when you basically draw it, you get the Ry, and then you get the angle here, right? So let's also look at the Z gate, and you'll understand when I'm saying that it will not rotate. So we are basically rotating along the Z axis. That's why it's just spinning around. So you can see a phase difference, but you cannot really see the arrow moving anywhere unless your initial state was somewhere in the between. So let's say if you want your initial state to be somewhere in the between, let me have circuit dot rx. Let me just put it pi by 2, and then we're going to have QR. So my initial state now is this, and now let me just rotate it around by pi. So now you'll see it just goes to Y. So this is spinning around this axis, right? And it's the same thing. You can have this RZ gate with this RZ denoting with the thing pi here. So now I'll show you a small representation. This is another library called as Blocksphere. It kind of does not work properly with annotations on this. So I've run this locally on my Jupyter notebook. So I'll quickly run the visualization. So if you see the X gate, see it's rotating along the X direction, right? And then when you see the Y gate, it's rotating around the Y direction. So this will kind of help you visualize how the qubit rotation happens. And this is the Z gate. This is why it explains when you are 0, it does not really, you cannot really see it. And then the Hadamard gate, if you see, let's just apply the Hadamard gate to, where's my, sorry. So Hadamard is also an rotation, but remember we do not have an angle here. It's all preset here, right? So I do not have to pass an angle here. I just do this. So yeah, you see it's coming here. So this is what was depicted in this part. The basic one was, the green one was up and then the blue one was on this plane. But when it rotated, it kind of is now interchanged, right? So this is what we are talking about, the rotation gates. Yeah, so you can basically have any kind of combination of gates made with these rotation gates. Right? That's why they are very powerful. They are very powerful tool which you should know about. So let me just go back to the presentation. What do we have next? So the next thing we have is the U-gate. I'm not going to demonstrate this because this is a bit more advanced concept. So U-gate is kind of like the general unitary gate, right? So it's kind of like the custom of custom gates. So you can have, while Rx, Ry, and Rz gates give you like specific rotation along those axes, a U gate will give you any arbitrary rotation along any axes, right? So you can have multiple axis rotations together. So that's why it's kind of powerful. You can use it when you have like you have like a very specific application here. So this is kind of very good in that case. So as you can see, you can also make any arbitrary unitary using the RZ, RY, and RX, RY, and RZ gate. Sorry for the typo here. So yeah. And if you were to make the poly standard gates, you can have this is basically the matrix representation of it. You have 3 parameters here which you have to pass. Remember, in the rotation gates, we used to pass just 1 parameter, right? But here you have to pass 3 parameters. So it's kind of a custom gate, like a really custom gate. So this is something you can read up on if you want. I'll not be demonstrating this, right? So let's go on to the next thing which we have here. The next thing which we have on our list is the concept of controlled gates. So I guess Freya had explained you about the CX gate, right? So the concept of control gate is basically you have 2 sets of elements in a control gate. So you have one set that's called as the control and the other set that's called the target. So the qubits that are control basically are the ones that, as it says in its name, control the output that happens at the target qubit. So unless and until the control qubits are active or in the state of 1, the target gate is not applied. So this is an example of a CNOT gate. So as you can see, this is the control line and this is the target line. When the control line is on, the target gate is applied only then and only then. So you might say, okay, can we have multiple controls? Why not? You can have something called as multiple control gates, which I'll be demonstrating to you right now. Right? So you can have multiple control lines which can be applied to one target, right? And there is also a possibility to have multiple targets too, but that's for another day. So let's just, I'll stop explaining and I'll start showing you how this thing works. So let's go back to our learning thing. Okay, what's happening? Give me 1 second, kind of hangs. So sorry about that. Okay, now it's working. Just my computer, sorry. So okay, let's start with making the circuit again. So I like to, as I said, I like to name my register. So I'll be naming my register as QR. So that will be quantum register. So I want 2 register now. So I want to demonstrate a normal control gate. And then let's have CR is equal to classical register. Okay. because I'll be performing a measurement to show you guys, right? So that's it. We have defined our circuit. Now let's apply the gates. Now we'll be applying the CX gate now, just to show you guys. So, okay, sorry, I have not defined the circuit. So circuit is equal to quantity circuit, and I'll be passing QR and CR. So we'll pass the qubits in the circuit, and that will make the circuit. And then we are passing the circuit dot CX. So remember, when you have a control gate, the first qubits are the control lines. The last one is generally the target line, right? So even you can scale it up to like multiple qubit gates. Is the first few qubits generally are the control qubits. The last one is the target one. So let's say I want to have the control at 0 and I have the target at 1. Let me just apply QR 0 and then QR1, right? So now I'll just apply a measurement. So I'll have the QR measured into CR, and then let me just, okay, sorry, I have already measured it. So sorry for that. But if you see it, it basically runs like this. Now, let's say I want to flip roles. Um, I want the first qubit to be my control and the 0th qubit to be my target. I can do that. So that's totally possible, right? Now, there are also a few other controlled rotation gates. So we can have like CRX gate, but remember it's an RX gate. So you'll need to pass in another parameter that's called, let's say, angle, right? So I want to rotate by pi by 2. And then my control is, let's say, 0 and my target is 1. Remember, the control will be on the first side of initializing thing in Qiskit. So if you run this, see, we have a controlled rotation gate. So right now we are just dealing with a single controlled rotation gates. I'll show you about multiple control gates in the next section. So this is what is about custom control, is about control gates, right? So you also have something called as a CCX, that's a Toffoli gate. You have like 2 controls and one like one target. So, oh, I'm sorry, we have not really made a bigger circuit right now. So let's just have a bigger circuit, 3 qubits. So I'll be showing you about 0 is control, 1 is target, and then we have 2 here, right? Okay, something's wrong, I guess. Okay, I forgot a bracket. There you go. We have a multiple control gate, right? So this is kind of an amazing thing. You can control the output of another qubit using another qubit. So this is kind of useful too. So let's look at what we have next. Okay, I think I should have, yeah. So yeah, this is also one more thing that I wanted to also explain is about the controlled custom gates, right? So it's not just it's not just that you can have one control like what I showed you there. You can have multiple controls. Okay, so we just have to make a big enough circuit and need to know how to implement that. So here what we do is, instead of having standard gates, we are basically getting gates from this documentation, this library, this specific place. So I have opened this up. So these are the gates that we have at our disposal that we can directly use and we can directly implement, right? So here I am demonstrating you about the H gate and RX gate. That's why I've imported the H gate and RX gate. So first, the very first step that we have to do to make a custom control gate is, first we have to define the gate, right? It's not that we can directly call it. First, we are defining the gate. So first I'm going to define the gate with custom. Let me name the gate as custom. You can name it any gate you want. So I'm going to use an RX gate first, right? So I'm going to add in a custom RX gate, and it's an RX gate. So we need to put in an angle. So I'm going to put in an angle of pi by 2. Then I'm going to specify something called as the control parameter. Now, in this parameter, I basically specify how many control qubits I have, right? So in the old CX gate, we had just one control qubit. Now I will be specifying how much ever I want. In this case, let's say I'm kind of feeling generous. I'm going to have 3 control gates, right? So now we have defined this gate. We need to apply it to a circuit, and to apply it to the circuit, we first make the circuit, right? So let me just name a new circuit that will be QC2 is equal to, let's say, quantum circuit. So remember, now the amount of qubits will be the control gate plus the target gate. So we have 3 control gates plus 1 target gate. So we are going to add in four qubits here, right? And then what we're going to do is something called as append the custom gate to the circuit, right? So that's what is done by the append operation. So what we do is we press in qc.2 append, and then we pass in 2 parameters here. So the first parameter is we pass in the custom gate that we have made, right? So I'll pass in custom as our gate. Okay, so the next thing which we are going to do is we are going to pass in the list of qubits that are going to act as the control and target. Remember when I told you that the first set of gates are usually the control and the last is the target? The same applies here. So I'm going to pass in, let's say, 0, 1, 2, and 4 as my control gates. And then I want to have the third qubit as my target. Okay, so you are expecting to have like a 4 qubit circuit in which the 0th, first, and the first, second, and the fourth qubits are being controlled, are acting as the control line, and it's being applied on the third qubit. So let's just look at how it's going to look. So qc2 dot draw output is equal to, let's have a beautiful output. Okay, something's wrong. What's wrong? Index out of range 0, 1, 2. Okay, I think I did something wrong here. Oh, okay, sorry. We had just 3. We had just 4. I passed in 3. I'm sorry. So remember, it starts with 0. You can also fall for it. So I'm so sorry about that. But yes, in this case, what's happening is the 0th, first, and the second qubit are the control lines, and the third qubit is the target line. So let's say I want to shuffle things up. Let's say 2, 1, and let's say first is this. So now my 0th, second, and the third qubit are going to act as the control lines, and the first qubit, this qubit, will act as the target. So you can see basically it's really kind of convenient to make really custom control gates, right? So let's say I want to increase this. I want to have 4 controls. Can have 4 controls. Let's say I do not want to have an RX. I want to have an Hadamard gate, right? I want to have a controlled Hadamard gate. So I put in H gate. And then I do not really pass an angle because Hadamard gate angles are already set. And remember, we need to change our circuit too. So 4 controls plus 1 target, that will be 5. So let's say I want to have 0, 2, 3, 1. What is left? We are left with 4. So 4th will be our target, and the other 3 are going to be our control. There you go. It's a 5 qubit Hadamard control gate that you can have, and it's going to only apply if all the 4 preceding qubits are active, right? So this is one thing that you should also know. Some complex algorithms might require you to do this. You can keep this in mind. Also, there's also one thing where you can make the whole circuit as a custom gate. I mean, I'm not really covering that, but you remember, if you do not just want to have separate gates, you can have a set of gates. You can kind of make them as a circuit and then package it as a complete controlled gate. So that is also possible that you can look into if the need comes in, right? So let's look, what else do we have on our agenda now? So the next thing that we have is importing the composer. So remember the Qiskit composer that was there? It's a pretty nifty thing. You can basically drag and drop your gates, and that thing basically generates the code for you too. So why not have it inside the notebook? So that's what IBM has done. They have created a widget which you can kind of import inside the Jupyter notebook and have it make all the gates for you, right? So let's quickly look at that too, shall we? So yes, importing the composer. So how you basically import the composer is, first you have to call the composer. So you have this import statement from IBM underscore quantum underscore widgets, you import the circuit composer, and then you specify a variable in which you have the circuit composer. Then you call the variable. It's as simple as that. When you run the cell, there you see you have the composer ready here. I can start dragging and dropping gates. See so many gates here. So I'll start putting just any random number of gates. It's kind of a nightmare to write all this code. So what if I told you that this thing will generate code for you on its own? All I do need to do is click this tick mark here. There we go. It has generated the whole code. And the best part about this is it updates automatically. So I press delete, delete, delete. It has become shorter now. So this thing basically updates and synchronizes with this, and you can have like the circuit basically automatically made for you. Now there has to be a catch, right? I mean, things can't be so easy. So the catch here is these variable names and the assignments are kind of fixed. So the names you cannot really change. If you change anything in it, let's say I am adding circuit dot x, let's say they have named it as qreg q0. I'm applying a x gate here, but this will not run because when I press an rx gate, my x gate just went away, right? I had typed in here on top circuit.x qreg 0. It has run away because this thing kind of does not take inputs in and displays it. So it's the other way around. You put the inputs here and then you get the output here, right? And yeah, you can copy and paste this somewhere else and maybe change the variables, and kind of good to, suppose you're not really feeling, you don't really want to code and you want this thing to do its on its own. So that's a nifty thing you can have. So that's about the composer part. Let's look at something else. So what do we have now? Backends. So here's where we come to the concept of backends. Now you learned about how to do your quantum circuits, you learned a bit about different types of gates, but what you're really doing is you are really applying it to something, right? So you want it to apply it to some kind of hardware. If you're running a normal Python script, it generally runs on your laptop, which has a CPU processor, right? So you need something to run these quantum gates on a inherently quantum device. So that's called a quantum backend. That's called a backend, right? Now the backend can be anything. So the backend can be a quantum device. It can be a simulator too. So what are simulators and why do you need simulators? So now imagine this, you're making a quantum device. Let's say you're making a quantum chip. Now you want to know that what the chip I'm making, is it giving me the right result, right? So you want to basically compare it with something. So what you do is you kind of emulate the quantum mechanical behavior on a classical system. So how you do that is by applying gates mathematically. So the matrices part, which Lokesh and Shivani had explained in the mathematical part, you basically run your circuit mathematically. You create like a mathematical kind of chain of operations which you apply to get the result which you would similarly get out of a quantum backend, right? So that's why you have these certain kind of simulators built into Qiskit, which you can use. And also not every time you can have like a quantum computer ready for you, right? So it's kind of convenient to have it on your laptop and you can run it anytime you want. Remember, Qiskit simulator runs classically. So it's kind of simulating a quantum system, right? And you know that quantum states are kind of, they grow really exponentially. So if you need to store those states on your PC, you need a lot of RAM. And it kind of grows exponentially to the fact that if you're using a lot of qubits, if you're even going close to 30, we are talking about using almost terabytes of RAM. So it's a good idea, if you're using a simulator, keep your qubits a bit less. I mean, right now there are a few efficient simulators that are coming up. You can also have like huge calculations on those. But yeah, that's a talk for another time. There are like Project Q and even Circ that do have, I think, higher number of qubits on your laptop, right? So Let's talk about the simulators that we are looking at today. So we are going to look at 3 simulators today. We are going to look at chasm simulator, state vector simulator, and unitary simulator. So chasm simulator is basically a quantum simulator. So what it basically does is it kind of simulates the circuit as if you're running it on a quantum computer. And the word here is it's going to run on a perfect quantum computer, right? So it's going to simulate as if you're running in a quantum computer without any noise or disturbance. So most of the time you'll get like a perfect result out. So let's say if you want to look at a state 0, 0, you're going to get 0, 0 out instead of, let's say, you're getting 99% of 0, 0, 2% of 0, 1. Sorry, my math is bad. So 94% of 0, 0, let's say 2% of 0, 1, 2% of 0, 1, 0, and let's say 2% of 1, 1, right? So instead of that, that's normally what you'll get on a real quantum computer. Chasm simulator will kind of simulate as if the state which you want after measurement is kind of similar to what you want, right? So there's another point here that it does this with a certain degree of randomness. So if you notice, when Freya was running the Hadamard gate, you were not really getting 50-50 as you expect. So there is certain degree of randomness that is baked into this simulator, which is kind of helpful because it's kind of running like a simulator, right? Also, there's also one more kind of addition to it. It's like if you want to simulate a real quantum computer, you can kind of pass in a variable called as a noise model, which kind of mimics the backend which we are having in the real IBM quantum this services. So like Freya had run on a real quantum backend, you can kind of simulate the same noisy behavior by copying the noise model from that backend. So that's also available here. We're not really looking into that now, but we'll just simulate the chasm circuit, right? The next thing we have is a state vector simulator. So let's say you are making circuits and you want to confirm what state you're in, or you want to confirm if you're going in the right direction. You can look at the state vector of the simulator, but here's the thing: you can only look at this when you are working on a simulator, right? Because remember, when you want to look at a state vector, you're basically traversing through through the gate operations, and you are basically getting the state of the whole circuit, right? So it involves you looking at the circuit. So that's kind of not allowed. So when you kind of look at the circuit or measure the circuit, kind of destroying the state. So this does not really run on a real quantum device. Okay, you cannot really get a state vector out. You can get a measurement out. Okay. So also, there's one interesting thing to note, that the chasm simulator I told you kind of behaves like a perfect quantum computer. So it in that let's say in that respect, even if you ask the chasm simulator for a state vector, it will not give you. It will just say, no, I'm a quantum computer, I'm not going to give you the state vector, even though it's a simulator. So that's very interesting. The next is the unitary simulator. So it kind of gives you back the unitary of the matrix resulting in the circuit. So all, as you know, circuits can be expressed as a huge unitary matrix, and it kind of becomes big and really, really cumbersome as you have more qubits. So you can have this nifty thing, unitary simulator, to kind of get you out the matrix after you apply the gates. And as usual, this is also involving traversing to each state. So this won't really work on a real quantum computer. You cannot really get a unitary out. So the same thing with chasm. If you ask it for the unitary, it will not really give you the unitary out, right? So let's look at how this thing works, right? So I'll just give me 1 second. Okay. Just takes time when I shift things. Okay. So there we go. There we know backends. So I'm going to be lazy and I'm going to use the circuit composer back, which we made up there to kind of make a circuit. So let's make like a simple circuit and make 2 head mods, and let me just measure these 2 head mods. Done. Okay. So I'm going to have the circuit made and I'm going to run the circuit. So remember, my variables are the register is QREG, classical register is CREG, and your circuit is circuit. And then now let me just print the backend, right? So I want to see how many backends I have access to. So you can do this from this nifty function, like backend in air.backends. And then if you print backend.name, you can see how many simulators you have at your disposal. So the ones which we are interested in are these three. So you have these other simulators which are kind of a bit advanced. So we will also kind of look into the air simulator very shortly in one of the mini projects. And then you have basically a simulator for most of the purposes, for density matrices, stabilizers, whatnot, right? So we'll just focus on the basic three here, which is kind of the backbone of a lot of operations, right? So let's just focus on this. So the main idea here is, I have just posted in 3 comments, is you first define a backend, you give the backend a job, and then you retrieve the results from the job, right? So this is how I like to break it up. You can make it in more compact way, agreed, but I like to break it up to kind of remember things much easier. So first I would define a backend, I would give the backend a job, and then I would retrieve results from the backend, right? So let me just have some backends. I will, since I'm demonstrating you 3 backends, so I'll just name it as backend 1. So the first backend I want to define is, first I'll just define the backend, right? So the backend lies in air. So I'm going to define air dot get backend. And first I'll demonstrate the chasm simulator. Okay, so let's just add in chasm underscore simulator. So right now the backend is defined inside this variable. So now the next thing I told you is we define jobs, right? We have to give backend some job. So what are we giving? So let's just see that. So job 1, I am not denoting the first job as job 1. I'm going to pass in an execution function. So you want the job to be executed, right? So execute. What are we executing? We are executing the quantum circuit which we made. So what is the name of the circuit? The name of the circuit is circuit. Okay, so we are executing the circuit. But what are we executing the circuit on? So we are executing the circuit on our backend 1. So I'm going to define backend 1. Okay, there's another concept here called as shots. Okay, so I'm going to put here 1024 shots. So what is the concept of shots? So as you saw in a lot of the previous lectures, that when you apply a gate, you don't really get an exact result. You get a probability distribution. You get the amount of, you get basically the probability result of the amount of time it's going to be 0 and the amount of time it's going to be 1, right? So the idea of short is it kind of runs it that many times and it gives you the result it got every time. Because what happens is, let's say I apply an RX gate with a certain rotation, which gives me 0 80% of the time and 120% of the time. If I run it once, I'm not guaranteed which I'm going to get, right? It could be 0, it could be 1. So you want to know what distribution is there. That's why you kind of have this shots function here, right? So we have done the shots here, and then we have, okay, so we have assigned the job. Let's kind of assign the result. Let's kind of get the result. So I'm going to give it as result 1 is equal to job 1 dot result. Okay, so that's it. So what we are doing is we have defined the backend, we have given the job to the backend, and now we are getting the result from the job. Okay, so that's basically what the steps we have done. And then let's get the outputs out, right? So our output would be basically counts. Okay, so we are giving how many times we are getting a certain output. So I am going to have, let's name it as outcounts is equal to result 1 dot get counts. Okay, so basically we are getting this get counts thing. Okay, result 1. Okay, I have typed it a bit wrong and I have not really executed this. Okay, so let's run this. Okay, we have got our counts. Now let me just demonstrate how it's going to look, right? So we're going to look at what result we have got. So let's just simply print the counts. We have stored it in out counts. So we're just going to print the out counts. So this is what you get, basically a dictionary with your the probabilities of the state, how many times it's getting right? So if you want to visualize it a kind of bit better, we can have like a histogram. So plot histogram, we can have, let's say out counts are variable, and we can give it equal. Okay, I just messed up the coding part, so sorry. It's gonna run. Okay, I'm so sorry. I think I have not really defined the plot histogram part, right? So what we do is basically let's import the plot histogram thing. So from qiskit.tools.visualization, I think yes, it's there. Import plot histogram. Okay, so should be posting now. This is weird. This should not be happening actually. Give me 1 second. Hmm. Okay, I kind of try to restart the kernel. Let's just try if it works like that. Because yeah, I have imported plot histogram too. Okay, so our editors here. Let's have Adamad here. Let's synchronize. I'm gonna run this cell. Okay, backend names, backend one, execute, job, and result, outcomes. Okay, sorry, this did not. So sorry about this. It's probably something that I have not really defined. So yes, we have not defined air. Right.
Vishal,
You
the spelling of histogram is wrong. Just check that, please.
Oh yeah. Okay. I guess that's what's troubling. Should have checked that first. So sorry. Oh, sorry. So yeah, you have to measure. Always remember when you're using a chasm simulator, you have to measure stuff to get counts, right? So I'm so sorry about that. So sorry for the small hiccup. Yeah, there we go. We've got the count. So that's what we expect. Basically, we are expecting an almost equal probability of all these states because we are having like two Hadamard gates. And when we apply the measurement, we're going to have like a truly random system here, right? So that's something that we are having. So now let's say I want to know what is the state vector of this, right? So I'll be showing you how to use the state vector simulator. So let me just comment out the first backend. Let's have the second backend here. So let me name backend 2. Remember what we do? First, we define the backend, give it a job, and then get the result out, right? So let's have air dot get backend. That's going to be the state vector simulator. Yep. So let's have the second job here. Job 2 is equal to execute circuit, comma, backend 2. So here we're not really giving any shots because the thing is that this is kind of not really a quantum operation, and we don't really need shots in this. We are not really getting something out, right? We're just getting a matrix out. So it's not going to have probabilities, right? So let me just comment out the result part too, and then let's have result 2 is equal to job 2 dot solve. Okay, so let me run all these three. Now here, I'm not going to run this. I'm going to run something else here. So there, if you kind of remember, we kind of got out the output state, right? So here we're going to get output counts. So we're going to have like out state sorry, there we had counts. Now we're going to get output state here. So there we had it. So out state is equal to result 2 dot, instead of get counts, we are having get state vector. Yeah. And then we're going to pass in our circuit. So the circuit's name was circuit. And this is an optional argument. So I noticed that when you pass in the state vector, you're getting like a very big string of decimals. So a lot of those are significant. So you can restrict them to like 3 decimals. Okay. So this is what you get. And then let's just print the out state. When you print it, you get the state vector. Now notice we have measured here. That's why you're getting a measurement state vector. So if I were to, let's say, remove the measurement, I'll get the actual state vector, which it should be expecting. So let me just run this one more time. So yes, that is the state vector, which we're expecting, equal probabilities of all these states, right? So this is kind of a nifty thing. And if you want to visualize it, you can have something called as the plot state city. So you can have visualization, 3D visualization of that. So for that, let's just from Qiskit.tools.visualization, let's import plot state city. Right. So we have imported plot state city. So let's just plot the plot state city for this state. So plot state city, and I'm going to pass in the out state. Right. Okay. It's not output, out state. And then let me just name it like state vector. So there you go. You have got like kind of like a visualization of it in the 3D space. So if you see the left hand side represents all the real values of the state vector. So you have like 0.5 as real, 0.5, 0.5. And yeah, about this J thing, just remember in Python, we are kind of following the physicist principle. We are not really having I as our imaginary part. We are kind of denoting it using J here. So 0J is kind of no imaginary part in this state, right? So everywhere there's no imaginary part, we are having no imaginary amplitudes here, this stage. As you can see in the second half, the right part of the plot city, which denotes the imaginary part, we're not really having any amplitudes here. If you were to change the circuit, you will definitely get it, right? So the next thing we're gonna do is the next backend we're gonna look into is the unitary backend, right? So backend is equal to air dot get backend. So unitary simulator. We follow the same set rules. We kind of have like we are kind of defining the backend. Then we basically tell what job we are gonna do, and then we're gonna get the result out. So I'm gonna comment this out, and you can have job 3 is equal to air. Execute. What are we executing? We are executing circuit, and then we are executing it on backend 3. So remember, we do not also have to give shots here because this is not really possible on a quantum computer, right? So let's also have result 3 is equal to job 3 dot result, right? Okay, so let me just run this quickly. Okay, so this has been done. Now I want to get the unitary out, right? So to kind of get the unitary out, we kind of can just call the output state unitary, right? So we are staying out state out unitary, sorry, equal to result 3 dot get unitary. So now our unitary state in unitary is going to be saved here, and then now let's just print it out. So print circuit unitary is equal to, let's give it a space to be neat, and then we can have like out unitary. So that's the unitary that's printed out. Okay, and then let's yeah, there's no visualization, and let's say kind of there's kind of no visualization per se in this. So Yeah, I don't think that there's any visualization with respect to this thing. And yeah, this is what I was talking about, the weird decimal thing. So e raised to minus 17, kind of not something that we want. So let's just remove it. So decimal, we'll just define decimal is equal to 3. And now we get a much more cleaner output. So, okay. Hmm. Decimals, sorry. Yes. So now you see the output is much more cleaner, right? Uh, yeah, that's it about the unitary matrix. So let's say I want to run it on a real backend. Okay, so I want to run it on the IBM quantum computer. So how do we do that? Okay, let's start with running this same circuit on the quantum computer. Remember, we removed the measurement, so let's bring back the measurements. I want some measurements also. Okay, let's run the cell. We'll not run all these cell, and let's make kind of a new cell. So I've already imported stuff here. So I've imported IBM Q, Air, assemble, transpile, and then I'll talk a little bit about what this least busy is, right? So first, what we need to do is first we need to set provider, right? So first we set the provider. Let's say provider is equal to IBM Q dot load account here, and then how to just get the provider here. So IBM dash Q. It's not underscores Q. We have to do dash Q. Okay. So when we run this, basically, okay, I'll just this on another cell. It will just show you that yes, we have kind of access to this. Okay. Let's see. Okay. It did not really print. It's fine. So now if you noticed before, we had defined like a specific IBM Q backend, right, from all these backends. So if you wish to look at the backends, you can basically look at your quantum services. And if you can see the systems which you have in your hand, these are not really all accessible to you. So if you click on your systems, you'll get what kind of systems you have in your hand. You can just take any name from this and have this. But what happens is basically you have a queue of things, right? So let me just, okay, so if you see here, there are total pending jobs here, 11 jobs. So if you see in other backends too, there are like different types, 126 jobs. So you don't really, it's not really possible for you to just go and search each one of them like, hey, is this available? Is this slow? So IBM has kind of given you a neat nifty function called as the least busy function. Okay, so here's what I'm gonna define it. So the least busy function, as it says, what it basically does is it kind of finds the least busiest backends from all the backends that are available based on what filter you apply, right? So let me just demonstrate how it works. So we call in least busy, and we basically give it the backend of what provider we are using, right? So providers dot backends. So remember we had set the provider as IBM Q. It's not just restricted to IBM Q. You can have different backends, like you can have Ion Q or Honeywell. That's, I guess, supported right now. So right now we are using IBM Q. That's available for us. So let's have some filters. So what this basically does is it finds the least busy backend irrespective of whether the circuit, irrespective of the number of qubits of the circuit. So let's say in our services, we have this IBM Q RMonk, which is a 1 qubit system. If it's less busy, it will basically redirect you to that. If you don't really specify anything, it will redirect you to RMonk, irrespective of whether you have 1 qubit in your circuit or not. So here we have 2 qubits in our circuit, and this backend just supports 1 qubit. We are going to have an error, right? So we do not want to have that error. So that's why we are specifying something called as filters. So let's have a filter function. So say filters is equal to lambda x. So this is kind of a lambda function, which kind of maps everything what I'm going to type after this to this variable x, and it's going to pass on to filters. So let's say first we need to specify how many qubits are there. So you specify it using something called as the configurations also. X dot configurations is dot n qubits is greater than equal to 2. So we have a 2 qubit circuit, I assume. Yeah, we have a 2 qubit circuit. So we want something that is greater than 2. So bare minimum is 2. If it's even bigger than 2, it's fine, right? It's going to run. So, and let's have some more conditions. And we want it to not be a simulator. So if you see in your quantum services, you also have something called as simulators here. So there is a chance that it might be redirected to these guys. So least busy basically finds anything what is available, right? So it will just redirect you to the chasm simulator. So you do not want that, right? So we are going to specify that it should not be a simulator. So how do we do is we add in a not operation. So not x dot configuration dot simulator. So what this will do is basically say that, okay, only give me the value if it's not a simulator. Okay. And the next thing is we have to check whether the backend which the least busy function has selected is kind of operational or not, right? So what happens most of the times is these computers are running like 24/7, and sometimes you have maintenance runs that can go for a few hours. What if the backend, if the least busy function just picks up a backend which happens to be um, in maintenance phase, right? So your circuit won't run and you'll be waiting forever for like weeks or I guess hours. That's not pleasant. So let's not have that. So let's have this x dot status dot operational equal to true. So what it's going to do is it's going to check, okay, is it operational or not? And then, okay, so that's what it does. So we have defined a backend here. So just to print that, is it running or not? Running on current least busy device. Let's say I want to see which device it's running, right? So device, it's going to give you which device it's going to run, right? The next thing we are doing is, as Priya might have mentioned, is the job monitor. So what happens is basically these computers, even though I'm kind of finding the least busy backend, sometimes you need to know, right? You need to get to know that how much you have to wait for your next job. So it kind of gives you the queue of how many jobs are there and gives you the result that, okay, is your job done or not? So that's why we are having a job monitor. And the next thing we are doing is something called as transpilation. So remember, these backends basically, the concept here is these backends have something called as basis gates. So these backends can understand only these basis gates. So what it will kind of do is whatever gates you are applying on the IBM quantum on your, when you're making your circuit, it will convert it into an equivalent of these gates. So if you, I'll show you the circuit too. It's kind of it kind of makes a very nasty circuit. And the best part is you do not have to worry about that. That can be done all by a simple function call. Okay, so that's what we are going to do. So we are going to set up a transpiled circuit. So transpiled is equal to transpile. That's the function. What are we transpiling? We are transpiling the circuit. We are transpiling the circuit for what? So we have to specify which device we have to transpile, right? So because if you see at the backends here, this backend has CX, ID, RZ, SX, and X. But let's say if I see another backend, it might have something else. Okay, this has the same too. Maybe something different. Okay, all have the same. Okay, all seem to have the same basis case for now, but sometimes it's kind of different in different systems. So okay, I'm not really finding anything that's kind of different here, right? Yeah, this does not have CZ or any other gate. So this is kind of, it just has this. So we have to specify for what we are transpiling it. So it will kind of optimize the circuit according to that. So we're going to have pass the device to this function. Then let's have a certain level of optimization. Kind of optimizes up to certain levels. I'm not going to go into this. This is a little bit in depth. So it's going to optimize basically according to some level. It's going to basically convert into certain types of gates in a certain way. So as we did, okay, we have basically set our backend here. So let's set our job. So job will be here, instead of execute, we are doing run. Okay, so we are giving it the device, and then we are running it using the device. So we are basically passing instead of your backend.execute, we are having like device.run. Okay, and what are we running? We are running our transpired circuit. Okay, and it's a quantum computer. So you remember we had passed in shots too. So here also we are passing in shots. Let's say I want to pass in 1024 shots. Okay, then let's have the job monitor. So what the job monitor will give me an output is what has happened of my job. It will give me an update what's happening of the job, right? And then we have interval is equal to 2, so it's gonna ping on certain intervals, right? So then we define the results is equal to job dot result, and then let's get the counts out. So counts is equal to results dot get counts. Counts of we're getting points of the circuit, and let's just plot the histogram of the circuit. Okay. So hopefully I have not made any. Okay, I have made a mistake. Okay, it's not configurations, it's configuration. My mistake. Now you should be running. So yes, it has found that the least busy device is Athens. Interval. Okay, it's interval. Sorry. Okay, typos. So yes, it found that IBM Q Manila is the least busiest backend, and okay, we are lucky. Job queue is not that high. It's just one, so it should be done in a few seconds. Hopefully, fingers crossed. So that's what it basically does, is it automatically finds whichever is the least busy, and you just don't have to keep searching which one is which, right? So come on, work. We just wait for a few seconds. So fun fact, you can also look at your jobs here on your dashboard, whatever jobs you have passed. So you get all your jobs which you have done, right? So it kind of comes here. Okay, it's still in queue. It's kind of happy. Sometimes there's some person all across the world that's sending a little bit bigger circuit. So it kind of takes time to kind of simulate. Remember, there are people all around the world that are simulating this, right? It's kind of, let's just wait, it's actively running. So kind of see. Okay. Okay, there's a new job result. That means this should be coming up soon. Okay, another job successfully run. There you go. So if you see our histogram results, this was from the chasm, and this is from the real quantum computer. You will always have some kind of discrepancies. Now, this is kind of a complete random result. That's why you cannot really see the discrepancy that much. You are almost expecting everything to be 0.25, but yeah, we are kind of close to that. But let's say if I were to simulate something else, a specific output, let's say I want to get 1 1, there's possibility that you might not just get 1 1. You get 0 0, a certain percent of 0 0, certain percent of 0 1, certain percent of 1 0, which is where we come to the concept of noise. So qubits, the kind of quantum system which it runs on is kind of very fragile. It has to be isolated. So if there's any kind of background disturbance, you're kind of measuring the system in some way. So what happens is kind of the state kind of decays and kind of has something called as decoherence. So it kind of decays down into another state which you don't really want. So you don't really want much interference. And right now there is a lot of research going on to mitigate these errors. So we have a lot of software methods to mitigate errors. We have a lot of hardware methods to mitigate error to, kind of get closer to a perfect qubit. But yes, it's kind of work in progress, but still we are kind of getting kind of good results here. So thumbs up for that. So yeah, let's go back to what we were doing, right? So let's go to, yeah, we have run it on a real quantum backend, and we looked at a short example how we ran the circuit. We got the backends. We also get to know how to use the least busy function to kind of get things out much more easier, right? So let's head on to our mini project then. This is exciting. So this is based on the operation that I did just now. So you might say, okay, you got a random result out. Why are you getting a random result out? I mean, Vishal, isn't there a function called in NumPy that gets you the random result out? Or you have the random.rand function? Why not use that? So it turns out when you generate random numbers in your system, it follows a certain mathematical model, and it is after a certain random seed that is generated. The idea here is the sequence of distribution, the sequence of numbers that is generated depends on that seed. The problem here is, yes, you can get really, really good random results out. Don't get me wrong, you don't really need perfectly random result for every implementation, provided the result is kind of implemented in a proper way. But the problem is that if you have the same seed with which the string of results which you have generated, the list of numbers which you have generated, if someone else has the same seed, there is a great probability that the other person can also get similar string of results, right? Which is kind of not desirable. You want something to be truly random. So that is something what we called as pseudo random numbers. What we generate on software is pseudo random, and it depends on a seed factor, right? So now what would you define truly random, right? So a true random generator is something that you get completely physically unpredictable. So a pseudo random number, remember that any mathematical pattern, if you follow it like long enough, there will be a certain pattern in it. Okay, so even if you have a random number generated with this, there will be a certain pattern that you will get if you follow long enough. Okay, so in some applications like cryptography, you don't really want that. You want something that is completely unpredictable. So what you do is you fall back to the phenomenon in natures, right? So quantum physical systems are inherently unpredictable. Okay, so let's say if we have something like thermal noise or something, let's say atmospheric uh, dispersion. So uh, previously, traditionally, to get like truly random result, we used to kind of uh, uh, get results out of these, like there were thermal noise random generators where you would get results out of it, right? But you don't really have, not everyone has that setup. So we have a quantum computer, and a quantum chip kind of follows the quantum mechanical system. Why not use that, right? So let's start with this thing, mini game, right? So I'll set you a premise of what we are basically making. Okay, so here's my second notebook here, which I can open. So what we are making is basically a quantum rock paper scissors game. So what we are doing is basically having kind of we are going to make it in like 3 sections. First, we are going to make our own section, the human section, where we are going to give an input to the game. And then we are going to make a quantum player. So the quantum player is going to be totally unpredictable. So we are going to use superposition principles to kind of get a really, really random result out. So if you might have seen a few implementations, it was kind of interesting that I saw that even when we play rock paper scissors, we have a certain bias when we kind of play the game, right? And even our choices are not completely random. And if you have like a machine learning algorithm that analyzes your games for a few tries, you can basically have that the machine learning model can probably beat you to every time, because it will kind of identify how the pattern of what you think. So let's have something that's completely random, that you cannot really, have things thinking, right? You cannot really predict what's happening. So that's how it is. Let's just start. So let's first set up the input, that is us, right? So first I'm gonna set something called as choices. So for a rock paper scissor game, any rock paper scissor game, we're gonna have three choices. That's rock, paper, and scissors, right? So let me just add it in a dictionary. So to recap what a dictionary is, a dictionary is basically uh, 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 think of it as a real dictionary. When you want to find the meaning of a word, you kind of search in the dictionary, and when you search the key or the keyword in your dictionary, it gives you the synonyms of that. So it's kind of the similar idea. You have keys and values. So when you look up the keys, you can get the values out of it. So I'm going to have rock as 1. Okay, I'm just going to assign numbers to each of these choices, right? So I'm going to have rock as 1, paper as, 2, and then we're going to have scissors as 3. So you need to have why is this happening? Sorry, butterfingers. Okay, so choices: rock, paper, scissors. So this is our dictionary that is comprising of these three choices. We have rock as 1, paper as 2, and scissor as 3. So let's kind of have common choices, and then let's start off with introductory comments. Like you like a bit of commentary. So we can have like, right? Welcome to the quantum rock paper scissors game. Okay, and then we can explanation just for fun. Print. Let's see. It's a challenge. You can have a wager. Okay, enter your choice. Okay, and just to make things neater, I'm gonna end it with a few blank lines. So what this function does is basically it ends it with whatever I enter after this. So I want 2 blank lines, so I'm going to use this. Okay, and then I'm going to get the user input. So user choice is equal to so we're going to use something called as the input function. So if you pass in the input function, it will ask you and store the output somewhere. So I'm going to store the output in user choice. Okay, so I'm going to have input as rock, paper, or scissors, and we're going to see so let's just okay, so since we have made this, let's just print our user choice and see what happens, right? So when we do this, okay, what have I, oh yeah, it should be outside this, sorry. So yeah, it kind of asks you a question. So you can enter rock, paper, scissors, so it will print out rock. Now I want to make this a bit more robust. So let's say, okay, first I'll just get in the value that is related with our dictionary, right? So I want 1 when rock is when I enter rock. I want 2 when I enter paper. I want 3 when I enter scissors. So what you do is basically store it in a variable called as choice index. What you do is basically you use the dot get function. Okay, so what happens is all our choices are inside a dictionary called as choices. So dot get, we are going to pass in the user choice. So what this is going to do is when we enter the input, it's going to store in user choice. And what it's going to do is it's going to compare this user choice with the values in the dictionary. And if it kind of matches, what it will do is basically it will return you what choice it matches, right? So in this case, I'll print choice index. let's say rock, paper, scissors. I enter rock. Okay, so it gave me 1, right? It searched for this and it gave me 1. What happens when I enter something else? Like, some random variable, it gives me none. So let's say I do not want this embarrassing situation. I want it to pester me all the time until it gives me a good input, right? So I'll put it under a while loop. So while choice index is equal to none, I'm going to basically use the tab to put it inside this while block. So what this will basically do is it's gonna check what the value of choice index is. So I mean, first I'll just initialize choice index to none. Okay, then okay. So what it's gonna do is it's gonna loop around till the choice index is not none, right? So that's the thing we are looking for. So if anyone enters an input that is different from rock, paper, or scissor, it's going to just ask again and again, enter something valid. Okay. I mean, I'm not really put a statement that's going to ask for enter something valid, but it's going to just pester you again and again, give a valid input. Okay. So just to make it a bit more resilient, I'll convert all the inputs which I enter into the lowercase so that even if you enter somewhat in the capital case, remember it kind of compares using the ASCII character. So the capital rock is not equal to small rock. So let's just convert everything to the lowercase for the simplicity sake. So let's see what happens. So it's going to ask me rock, paper, scissors, right? So I enter some random thing. It's going to ask me again, enter something better. So I enter another number. It's going to ask me again. So it's kind of resilient in that case. So I'm going to enter rock. Notice I have entered R capital. So even though I entered R capital, kind of works out. So right now we have printed the choice index, right? So our human player is ready, right? Now, what I want to do is I want to package this as a function, okay? So that I can call this code every time. I do not want to type all this code every time I want to call this, right? So I'm going to define this as human player. And then remember, Python kind of takes care of the indentation a lot. So you have to indent it. Easier way to indent is just tab and tab. So now it's inside this block, right? And if you want to go back, you just shift tab again. So it goes back. I want to keep it inside. So I'll just keep it inside here, right? So instead of printing choice index, I wanted to return the choice index because I want to use this number 1, 2, and 3 somewhere, right? To make things easier for me. So I'm going to do return. Okay. Choice. So what this is going to do is every time I call this, it's going to ask for an input and then it's going to return me the value that is corresponding to this dictionary. Okay. So that is what this function does. So if I run it now, it's not going to do anything because I'm not called it yet. So let's just keep it at that. So our human player is kind of done, right? So let's now it makes sense to make like our quantum player. So let's start with making our quantum player. Okay, so should I start directly? I'll start directly with functions. Okay, so I'll directly make a function here. So define quantum player. Okay. Define the quantum player. Then now I import statements. Okay, I want to import number as maybe I'll use that. But import pi from Qiskit, import circuit, and then execute. Want Airtel, I want a classical register because I am following the measurements, and then I want quantum register, right? So that's done. So now let's just define our circuit. Let's go. Oh shit. So yep. Okay. So as I told you, I like to name my register. So QR is equal to quantum register 2. Now there's another level to naming. So you can literally name the qubits what you want. So if you remember earlier, we used to get some random Q0 or QR or something, right? You can name it what you want. So I just name it as qubit. Remember the convention here is you have to have everything lowercase. Okay? So it follows something called as an open QASM standard. So in that case, you do not really have, if you put like a big Q, it kind of gives you an error. It's not according to the standard. So let's follow the standards here, right? So let's have classical register. classical register here will be, okay, two classical registers, and let's name it as the output, because that's our output, right? This is just for visualization sake. So circuit will be our quantum circuit. Okay. So RCR, we can also name the quantum circuit. So if you want to name it, you can name it. I like to name it. So now the idea here is we need to have everything very, very random, right? So what is the gate that puts things into randomness or puts things in superposition? That's the Hadamard gate. So guess what we are applying? We are applying Hadamard gates on two of our qubits. So circuit that H is equal to QR0. Okay. Circuit that H is equal to QR1. Okay, so we have done our Hadamard operation. Fun fact, you can just have circuit.h. Okay, guess we can visualize. Okay, have that. So let's have circuit. Oh. So if you see, you got two Hadamards here. There's another way to describe Hadamards for, let's say, all qubits in the circuit. So in that register, so you can just have circuit.hqr. So this will have the same effect. So, but remember, if you have like 3 qubits, it's going to apply to all 3 qubits. So this is not really, let's say if you want to apply to the whole quantum register, you can just, instead of passing individual lists, you can have this direct passing of the register to do the same. Okay, so let's go back to quantum. So yeah, okay. So we do not want to draw the output now here. So let's measure the circuit. We're gonna measure the circuit. We're gonna put the measurements of the quantum register into the classical register. So QR to CR. And now let's just define a backend. So for the interest of time, I'm kind of restricting ourselves to QASM simulator here, but you can of course change this later to run it on a real backend, right? So let's do that quickly. So what are the steps? You first initialize the backend, give it a job, get the result out. Okay, so we initialize the backend, that is air.get backend, and our simulator is QASM simulator. And then we're gonna have the job. So job is equal to execute. What are we executing? We are executing a circuit. Where are we executing? We are executing it on the backend. How many times are we executing? Let's say I want to execute it just one time because I want just one measurement out of it. I do not want a distribution of measurements. I just want one measurement. Every time I run this, I want one measurement. It can be anything because I'm looking for a random value. I don't mind if it's just one measurement. So I'm just passing shots as one. So result is equal to job dot result. Okay. And then what we're going to do is we're going to get the count. So, sorry, let's just let that mute. Then let's have like, let's convert the results to something we can understand, that is integers, right? So if you remember, the results which we used to get previously was as a dictionary. So I want to convert the dictionary into an integer. So first, let's just define counts as get the counts out. So gets is equal counts is equal to result dot get counts. Okay, so this will get me the count. Now I'll make an output variable. So the count is now a dictionary, and I want to convert the dictionary into a list. So what I do is I convert the dictionary into the list, right? And what do I want to convert is like the first value of it. So I guess it would be good if I kind of visualize it, right? So let me just, okay, let's do that thing at the end. Okay, and make the function at the end. So let me just print the counts and show you how it looks now. So it kind of looks like this. So you have got this result out. Okay, so I want to convert this into something I can get, right? Like I want to make this as an integer. So binary 10 is not really in our dictionary. I want it to be decimal, that is base 10. So I want to convert it now. So first I convert the dictionary into a list. So I'm gonna have output is equal to list counts dot keys. So what it's going to do is it's going to pass in the key values in there. Now I want the first key out of this. So let's see how this looks like. Right? Kind of looks like this. So I've got the binary result out. So I wanted this. I do not want how many times it came. I know it's one time because I had shots as one. So I'm going to get the binary out. Now I want to convert this binary into an integer. So we have a handy dandy int function for that. So let me save it into another variable called as quantum player. So quantum player will be integer. The output, which had the binary value, and then I'm going to convert this into decimal. So what this int function does is it basically asks what the basis of the input which you're giving, and it converts it into decimal. So now our input, which is the variable output, is of the base 2, right? So we are going to specify that, hey, function, this is base 2, convert it into decimal. Okay, so let's see what comes out. So if I print quantum player, okay, sorry. See, it prints an integer result out. Let's see. Let's see if we get something out. So 10 is 2, binary 2, right? So it's kind of do that. So it does that, right? So we have done this part now. Now let me remove the print statements. We will not be needing the print statements. Okay, there's one more thing here. Okay, we have 4 options. So if you notice, we have 2 qubits here. So 2 qubits means 0, 1, 2, 3. Yeah, 0, 1, 2, and 3. So we have 4 options here, but we have just 3 choices. That's 1, 2, 3, right? So we need to remove 1 choices out. So what we're going to do is we're going to kind of run this until in a loop until we get the good results out. So in the dictionary, what I've done is I've omitted 0. So so what I'm going to basically do is I'm going to make sure that if 0 comes, it runs the circuit again, right? So it's going to rerun the simulation and get you a different result out until you get a different result out. So how do I do that? So for that, I have to put the whole circuit, the execution part, in a while loop. So I'm going to put it as while to be like, okay, this is going somewhere weird. If you put this and do not have a break statement anywhere, it's going to basically run forever. Okay, so do not use this unless you're having a break statement here. So this is going to basically run forever until a specific condition is met. So what is that condition? So I'm going to set the condition. So the condition will be if quantum player, if you remember, quantum player is the decimal result that we got out of the counts. If quantum player is not equal to 0, I'm going to have reprint the quantum player's choice, right? So that will be our value choice, and we have quantum player. And then I'll be breaking it here. So what it's essentially doing is if there is a valid option, it's going to break the loop and it's going to come out of the loop, which is what we want, right? So if it's 0, it's going to just run again, right? So this condition will not be met and the loop will just go back again. But if the value is not 0, it's going to meet this condition and go inside this block and then execute this break statement. When it executes this break statement, it basically comes out. Okay, so now we have done this. Let's package it into a function. So I had done that before, but we had to demonstrate it. So I removed the function part. So I'm just going to define quantum player, and I'm going to put all of this inside the block using tab. And then I have to return this result, right? So I'll return the result that is quantum player. Done. Okay, am I in okay, indentation is very important in Python, guys. So if you're working with C, C++, Java, it's kind of not that important. You have blocks, but here the indentation are the blocks. So be careful with that. So if you have this here, it does not mean the same as if you're having this here. Okay, so yes, so let's see if we have any typos. Okay, it's not going to show up now. It's going to show up later. So now we have done our Okay, my PC has signed again. Okay, it's working now. So now we have made a human player and we have made a quantum player. Let's set the conditions for the game. So we have to check, right? So every game has a set of rules. We have to give the rules. So let's have the format as uh, quantum computers result. And so the reason why I'm using a dictionary is because it kind of makes it convenient to uh, get it to compare results out, right? So I'm gonna kind of make um, make a function that plays the game and then sets the condition for the game, right? So define play game. So let's have a dictionary called as result, which stores all the possible combinations. So the format is the first input will be the quantum computer's choice and the second input will be your choice, right? So as we know, we have to set up a certain few conditions. If you remember, one is rock, two is paper, and three is scissors, right? So one is rock, three is scissors, rock beats scissors. So in this case, who does win? Because one is chosen by quantum computer and two is chosen by us. Who wins is basically the quantum computer. So we can have something like beats scissors, quantum player wins. Okay, have a smiley or something. You can have it. So in the same case, let's have another condition. So paper and rock. So who wins? Paper wins. So in this case, also our quantum computer kind of wins, right? So something like tough luck. Help if I could type. Yeah. Then let's have another condition. That will be three is scissors and two is paper. So scissor beat paper. We have something here. Right. So we have this also. Similarly for other conditions, you have 3 and 1. So 3, 1 would be quantum computer chose scissors and you chose rock. Bad choice, quantum computer. So you're gonna win in that case. You will win. And then let's say what is another possibility is if you select paper and the quantum you select paper and the quantum computer selects rock. Again, quantum computer versus. Okay, so have something like this, anything, your wish. It's kind of custom. I'm just typing something. I think we have covered in all the possible combinations here, right? So now that we have made our rule, let's initialize the game. So we have to call the functions which we made above, right? We have to call the human player, we have to call the quantum player, and then we have to compare the results here. So what we're going to do is we're going to call the human player. So human choice, I'm going to store the result returned from the human player function into human choice. So we're going to call human player. So the syntax to call a function is basically the function name and then this. So our function name is this. So I'm going to call it like this, right? Next thing is, let's say, quantum player is using, okay? And player is equal to quantum computer. Okay. Right. Okay. No. Okay. I just. Okay, maybe we can. Because I had a issue with the names being same, so that's why I guess I changed it. Okay. So yeah, what this will basically do is first it will run the human player function. So it will ask input from us. Then it will run the quantum player function. It will basically measure input and get something out. And now what we have to do is basically compare it with the result dictionary, right? So what we're going to do is return result. Since it's a dictionary, we are kind of getting the result out of it. So we are going to compare everything, right? So results of .get will be, the format is, first it's a quantum computer and us. We have stored the result of a quantum computer into the quantum player. So we are passing the quantum player variable, and then we'll pass in the human choice variable, because that's the variable in which our choice is stored. Then you might notice that I have not really passed in the conditions for drawing. So what I'm assuming is, if it's not any of these, it's a draw. Okay, so that's what it does. So if it's not any of these, it's kind of gonna post that it's a draw. Okay, so have we messed up? Yeah, we have somewhere. Yeah, result is equal to, okay, so that's okay. I forgot one important thing is, you need to add commas everywhere. It's a dictionary, right? Last one you can skip, but everywhere else it's kind of like commas. So ran successfully. Now let's play the game. Okay, let's play the game. So welcome to the quantum rock paper scissors game. Let's see who will win this game. Enter your choice. What do you guys want to know? Rock. Quantum player is choosing. Okay, we have messed up somewhere. Oh yeah, we have to run the circuits. Sorry, we have to run the cells. We did not really run the cell. Yes, the quantum player chose. It chose 3. So okay, have we messed up somewhere? So quantum player choice is 3, 3, and 1. It's not a draw. Have I mapped it? Okay, so let's just run it once more. Missed anything? Might have missed something here. 1 3 2 1 3 2 3 1 1 2 2 3. Should be working. Human choice, human player, human choice. It's a draw. Result.get, quantum player choice. Okay. Best choice, it's a draw. Have I missed something? Okay, there seemed to be a small problem with the function. I can do one thing. I can, okay. Let's just kind of trace back what's happening. So it's not really going to the intended function as we want.
I think you've added a semicolon after break, so just check that.
Oh, we have to add a semicolon after break. No, that part is working. So it's somewhere where I have messed up. Your choice. Oh, I think I have choices.get user choice, return choice index. Seems to be a very small problem, which I think I need a little bit of a cool mind to work on. Kind of skipping. It's kind of skipping the result part for some reason. Okay, I guess let me just show you the one that I have already tested out. So I'll open the one which I made, which I'll upload in the GitHub. You can check it out. So it's basically the same functions. Not know where we have kind of missed it. So I rock choices 1, quantum player's choices 2. So quantum player chose I guess paper. So paper beats rock. Tough luck. So I'll kind of look into it and I'll post in Discord that where we kind of messed up. I am pretty sure it's kind of a very, very small error there. So this is basically the game. So I enter paper. My choice is 2. Quantum player's choice is 1. So quantum player chose rock. I beat the quantum player. So this is basically what it is. So all the choices which the quantum player is generating is completely random, and not random right now because we are using the chasm simulator. But if you change the back into the real quantum simulator, it will kind of trust me, it will be really random, right? So I guess it is a time for a 5-minute break, and then we'll kind of look into our next topic, that is quantum teleportation. So it's something that you might have heard in the like a buzzword somewhere. What is quantum teleportation? I'll kind of try to clear a few concepts of this, right? So let's have a 5-minute break, I guess, and give everyone a bit of a space for breathing. So let's be back. Countdown timer. Google has one, right? So 5 minutes, right? We'll be back. Okay. Thank you so much. Okay, I'm monitoring the chat. I'm so sorry. I was not really looking at the chat. A lot of people pointed out a lot of uh, uh, comments, and there are a lot of questions. Thank you for pointing out the mistakes. I'm so sorry. I cannot really see the chat when uh, I'm kind of presenting. So sorry about that. Kind of looking at using my mobile. Okay, we are back. That rest was kind of finished a little bit early. So yeah, um, let's keep on going then. Let's keep on going to the quantum teleportation part. So before that, thank you, Lokesh, for answering all the questions. I do not see any questions unanswered before the break. So if there's anything, please point me out in the Discord. Um, I'm going to answer a few questions I have got. So the first question that I have got is, could you please tell me the difference between generating random values by a classical and a quantum computer? So as I said, when you generate random values using a classical computer, you're basically following a set mathematical formula or uh, mathematical result out. So you use something called as a seed. So your result depends on the value of the seed. The caveat here is any mathematical straight random value string has kind of a pattern if you look long enough, right? I mean, it may not be apparent for, let's say, 1,000 or 2,000 digits, but if you look like really long enough, you will find some sort of pattern embedded in it. So and also one idea is that if you can get the seed of the uh, random number generator, your pseudo random, your classical random number generator, it's possible to basically recreate that result out, right? So uh, in a quantum computer, what you're basically doing is you are kind of putting the qubit in a superposition and measuring it. So you're making a quantum physical state and you're kind of measuring and collapsing the state. And the idea is that the quantum physical state here does not have a set, um, let's say, does not have a set path or an understanding by us, at least, that it's going to fall into 0 or 1, right? So it's going to collapse into one of these states, and we do not know which state it's going to collapse to because there is an equal probability of it collapsing. So that's the idea. In a quantum computer, you're basically having a physical phenomenon, a quantum mechanical phenomenon, getting you the result, and we're kind of interpreting it, the result in that way, right? I hope that answers your question. There's one more question I received. That's, can you explain the part result.get counts output is equal to, okay. So what I'm doing is, first, as you know, first we define the backend, then we pass the job, and then we pass the result. Now to get counts of the out of the results, we are basically using this function. So result.get counts, we are getting counts out of the results. So the next thing is, the result we are getting it is in a form of a dictionary. We don't really want a dictionary, we want something as a number. So to first convert it into a number, I want to first get the value of the first, get the key value of the dictionary. So what I'm basically doing is I'm kind of converting the dictionary into a coin, into counts. And the 0 here basically means that I'm taking the very first element of the dictionary, right? So that's what I want. So that's how it converts it into a list. The next thing I'm going to do is I'm going to convert it into an integer, which was the next thing. Do not worry about that. If you do not follow now, I will be posting these notebooks online on GitHub. I'll send you the link. You guys can experiment with it. I'll basically have the empty notebook too, and also the filled notebook too, right? So if you want, you can experiment around with it. Okay, so let's not waste any time and let's hope. Okay, my computer is working now. So let's look at the next topic. I hope everyone is recharged now, filled your coffee cups and refreshed now. The recording will be posted. You can come back again and check anytime. So not worry about that. So the next thing that we're looking into is quantum teleportation. A very, very buzzword, right? So it kind of sounds futuristic. You are teleporting something, and let me just break it there that no, we are not gonna be saying Scotty beam me up as of yet, right? So the idea here is you're not really transporting something physical, you're transporting information. Okay, you're transporting quantum information states from one place to another at very long distances. Okay, so let me just explain it to you with the storyline of Alice and Bob. So let's say we have two researchers, Alice and Bob. Okay, Alice stays in America, Bob stays in Russia. Okay, and both are researching on quantum computing and technologies. But unfortunately, these guys only have one classical phone line to contact with. Okay, so the phone line which they have can only transmit classical information. Okay, now the thing is they can talk to each other classically anyhow, but they're working on quantum computing and quantum technologies. They want to transfer their quantum data across each other, right? So sorry, I'm getting a few notifications that a few people are in the waiting room. So Lokesh, can you look into that? Hello.
Yeah,
Okay.
I admitted.
Yeah. Fine. Thank you, Freya. So, so where were we? Alice is in America. Bob is in Russia. They can only talk using a classical phone line. So, since they're researchers and they want to have, transfer quantum states, they call Telemon. Telemon is their friend, basically, who travels from America and Russia. So they basically send him a postal package every time. Okay, send this quantum state to Bob. Bob sends it to Alice. Now kind of Telemon basically worked around like a postman, and then he got kind of fed up with it. He's like, hey, I'm kind of fed up. I'm not gonna go around everywhere. So Alice and Bob are like, what can we do then? We just have a classical thing. We don't have a fiber optic or some quantum channel to basically send around the stuff, right? So Telemon says, okay, I'm gonna give you a protocol using which you are going to be able to transmit your quantum state across long distances. Okay, are you ready to listen to me? Alice and Bob say, okay. Let's just follow with it. So what does Telemon comes up with? So what basically Telemon says is that Telemon is going to entangle two qubits. He's going to entangle two qubits and he's going to give each one to Alice and Bob. So Alice and Bob is going to have one qubit each. So Telemon says to Alice that you're going to perform what is called as a Bell measurement, and you're going to pass the Bell measurement value to Bob. Okay, so if you remember, measurement is going to give you a classical result. And I told you they have a classical phone line, so they can send it to through classical phone line. So Telemon tells Alice, you do a Bell measurement with whatever quantum state you want to send, and then you send the classical result to Bob. And Telemon tells Bob that, hey, Bob, the result which Alice sends you, based on that, I'm going to give you a table and you're going to apply the gates corresponding to the result which you get. And if you would do the same, you won't be needing me, and I can stay and go on a vacation somewhere. So Telemon says that the entangled qubit, the entangled qubits which Alice he's going to give Alice and Bob, and the protocol which Telemon told Alice and Bob, he basically claims that we are going to be Alice is going to be able to send the quantum state to Bob without sending any qubit across, as they did with Telemon as a postman. So, well, Telemon is smart. He does not want to go around like a postman. And let's see if this thing works. So let's see into a bit deeper. So this is the basic idea behind it. So first you entangle two qubits, and then you can separate it and give it to two people. The idea here is these qubits have some sort of correlation between them, that when you perform a Bell basis measurement with whatever information you need to send across to the other person who has the other entangled qubit, if you only send the classical information out there, and based on the classical information, if he looks at this table and applies the gate there, he's going to get back the same state. Okay, that's the claim here. Okay, there's a bit of mathematics behind it. I don't think I can cover that. So I'll send in resources in the Discord channel, but let's look at the implementation part here. shall we? So the idea here is, if you remember, Telemon told Alice to kind of do a bell maces measurement and send bits to Bob, classical bits. So Telemon gives this table to Bob. He says, here are the bits received. If Alice sends you 00, do not do anything. Like it's an identity gate equal to doing nothing. And then Telemon says that if you get 01, you apply a single X gate. If you get 10, you apply a Z gate. And if you get 11, you apply a Z gate and an X gate. So this is what Telemon tells. This is the protocol that he says, right? So let's quickly look at the circuit, how it works. So here's what we are looking at. The second and the third qubit here are the qubits of Alice and Bob. Okay, so we are going to consider this as the qubit of Alice and Bob, and we are going to entangle this. This, if you remember, is the entangling circuit, right? So we entangle these we entangle these qubits, and then we can separate this out somewhere. Let's say this is Alice's qubit and this is Bob's qubit. So Bob is somewhere else, right? So Telemon delivers these qubit to these two. Now, what Alice does is something called as a bell measurement. So she applies this following gate set and she measures the value out of these gates. And when she measures this, she basically sends the measurement to Bob. Now, what Bob does is, based on the measurement, either if it's 0001, 1011, he applies the certain gate sets, X or Z gate, if you remember, in our gate set here, right? So he's going to do this basically application of gate. So this is the protocol. And what Telemon says is that the information state here, stored here, which was with Alice, is going to be magically teleported to Bob here in some way, right? So he's going to basically, he's saying that if you do this protocol, this information is going to end up here with Bob, okay? However far Bob is away, as long as he can as long as he can get the classical input out, you can kind of, Bob can get the state out. So you remember Alice and Bob had a classical phone line, so they can contact classically, right? So let's just look at the implementation. I guess that's the best way to do anything. I love to implement stuff. So quantum teleportation. So let me open the quantum teleportation notebook. Sorry. So yeah, I have imported a few libraries. We need math, we need pi, we need quantum circuit, register, classical register, transpile, air, execute. Basically our normal set of libraries. Okay, where's my cursor? Okay, let's see. Yeah. So after that, let's start with our circuit, right? Initial circuit. So we'll initialize this circuit components, right? So first, let's have 3 different qubits. So I'm going to name these qubits in certain ways so that you can visualize it very nicely, right? You can have any name to a quantum register or a classical register, but I'll kind of name it in a bit verbose way here. Okay, so I'm going to have state package is equal to quantum register. So 1, and then we're going to name it as state package, right? So state package is going to be our quantum data, which we want to teleport, right? So Alice has the data. She wants to send it to Bob. We're going to use this qubit as our information qubit. Okay, so now let's name Alice as a qubit. So quantum register, and I have 1, and name is equal to Alice. Remember, we are having the QASM naming format. Do not have any caps lock capital words in the naming. Okay, it's gonna throw an error. Okay, so we have Bob. Okay, so this is our circuit of Bob. This is our circuit of 3 qubits, right? If you notice, where are you presentation? If you notice, we had 3 qubits here. So the quantum state, our Alice's qubit and Bob's qubit, right? So where are you? Okay, so yes. Now let's also have output as a register. We do not need to name all the registers, so let's have name is equal to right. So we just initialize output is equal to quantum circuit. So we're gonna pass in state package. We're gonna pass in Alice. We're gonna pass in Bob, and we're gonna pass in output. Okay, so this will comprise of our circuit. You wanna look how it? You wanna see how it looks? So circuit.draw output is equal to MVN. So as you can see now, we have 3 qubits that's named state package, Alice, Bob, and output. That's our classical bits, right? So let's continue on. I want to send in the state package. Okay, before that, I'm going to give you a small note on how we are going to confirm this, right? So if you remember, this is the IBM quantum experience. And we're going to look at how state vectors are going to look, right? So here we are going to get the state vector out of whatever we are doing. So remember when we are looking at the graph here, okay, give me 1 second. Yeah, when we are looking at the graph here, we are basically looking at like this. So 0, 0, 0 is 0, 0, 0, 0, 0, 1 is 0, 0, 1. So if I show you 0, 0, 1, 0, 0, 1, right? Yeah, read it from the down to up. When you're reading this like this, you read it like this. Okay, so 0, 0, 1 is 0, 0, 1. Okay, so the claim is, I'm going to just demonstrate that if I have, let's say, a state that is Rx pi by 8, which kind of looks like this. Remember, you're having it in the first qubit, so it's going to only, you only have to look this part, right? So 0 and 1, that's the first qubit. That's why you're looking at this. Now, if you were in the second qubit, you would look at the middle part. So 0 and 1. So you're going to get this, right? Because it's the same state. Now, if we are having the third qubit, you're going to look at 0 and 1. Okay, we are not really caring about the other qubits, right? So this is how we are reading the state. So the claim here is that this state in the state vector is going to be teleported here. So this will become somewhat this, but it's going to have a kind of like a change like this. So this is not really shifting the state of the third qubit. Remember, after the measurement, after Alice performs the Bell measurement, we don't really care about those qubits now. We care about the state in the Bob. And if you look at this now, if you look at the same, this thing, you're basically seeing that, yes, it is still in the same state. You're getting the same state, albeit just the first qubit is going to have like a different shift, right? So if you remove this, it's the state 0, 0, 0, and then 1, 0, 0. This is just 0, 0, 1. So this gives you the probability of 0, and this gives the probability of 1. So if you see the block sphere representation of this kind of comes like on this side. So it's kind of close to 0. So intuitively, you can say that, yes, the probability of getting a 0 is much more, right? So the claim here is we are going to shift this state to this state, which is basically the same state of Rx pi by 8 applied on the third qubit without passing any Rx gates on the third qubit. We are just following the protocol. We are just passing the classical bits, and we are going to get the result out. That's the claim here. So I'm going to prove that, yes, this kind of works out, right? So first we prepare our state, like we prepare a state. I want to send a state to, like say Alice wants to send a state to Bob. So I'm going to prepare the state circuit.rx. Remember, we have to give like pi by 8 to Rx, right? So pi by 8, and then we're going to pass in the state package. So this is going to apply the Rx gate to the state package variable, the state package quantum register with an angle of pi by 8. So now just to make things neater, we are going to have circuit.barrier. Remember, just a fun fact that circuit.barrier is not just shown to for visualization, but also for transpilation. If you remember the small transpilation part I said, it kind of helps in that too. Just thing to be put out. So let me just print out how this kind of, okay. Oh, this has to be in quotes, right? So yes, so as you can see, okay, I have to run this again. Yeah, as you can see, we have applied the Rx gate and we have applied a barrier function here. Now let us entangle the qubit, right? So let's entangle Alice and Bob. So let's apply entangle and between Alice and Bob, right? So we're gonna have circuit. Remember, entanglement was Hadamard gate and C naught gate. It's not circuit dot G, sorry, circuit dot X, and we are H, and we are applying to Alice, and then we're gonna have circuit dot CX. So the control is gonna be Alice, and the target is gonna be Bob. Okay, so Alice, comma, Bob. If you want this for reference, so control is Alice and target is Bob, right? So Alice and Bob. We're gonna have circuit dot barrier, yeah. Then we're gonna have circuit dot drop output. Go to MPL so that we can just take a look what we did. Yeah, we have entangled this. So Telemon has entangled and he has given each of them a separate qubit now. Now, what do? We follow the protocol. Telemon tells Alice, you do a Bell basis measurement. So what is a Bell basis measurement? We basically apply a C naught gate and a Hadamard gate here, kind of opposite to this, right? So let's have a Bell measurement, and we can measure it also. Circuit.cx. So if you notice the Bell measurement, we have the state package as the control and the Alice as target. So state package as control and Alice as target, right? Then we have an Hadamard gate. It's going to be Hadamard on the state package. So then we're going to have circuit. Okay. Just make things a bit more neater. Okay, so there we go. We have almost completed the protocol. Now we are left with measuring the state, right? So we need to measure the state. We need to measure which qubits. We need to measure state, package, and Alice. What do we need to measure on? On the output qubits, right? So let's measure the state. So in this case, if you want to measure like this, so the idea here is to have two lists. So what happens is the elements in the first list are going to be the quantum registers, and it's going to be applied to the elements in the second list, that is the classical register. So our quantum register name was state package and say 0, and then Alice. We are applying this to the outputs, right? So output 0 and output 1, right? So let's just draw to confirm. Fun fact, if you want to look how it looks, okay. This is right now, I guess earlier what used to happen was if you did not put output.mpl, you used to get like a text-based representation, which was kind of fun too. So I was trying to find that, but yeah, I guess this is natively how it does now. Okay, so okay, if you notice two measurement here is nothing, just you run all the cells again, right? So if you run the cells again, kind of works. Okay, so now it works. So if you see, let's say you have some gates running twice when you kind of run the cell, is probably something stable. So you just run everything again. That works, right? So yeah. Now we have the Bell basis measurement, and Alice basically telephones Bob, and she's like, okay, this is the measurement I've got, 0, 1, or whatever measurement she got. Bob now has to apply the gates according to the table which we mentioned here. Where's the table? There's the table. I'm not sure if you can look at it. So this is the table basically which we are following, right? So 0, 0, 0, 1, 1, 0, 1, 1, right? So we have two options to do is basically get the measurement out and then use something called as a CF. I'll take a bit direct approach, and I'll just use a controlled gate, right? Because when you measure, after you measure, the state is not going to change. So if this was 0, this qubit is going to stay in a 0 state. Even though the state has collapsed, it's going to still stay in that state. So and even if this is 1, it's going to have the 1 state. It's not going to lose the state, right? So let's have just for neatness sakes. And then, so first we have to have a control Z. When do we have to have a control Z? When it is 1. So whenever it is 1, we have to have the control Z. So I'm going to apply a control Z to the state package. So control CZ is equal to state package and pop, right? Then we have to apply the X key, right? So control X, we have to apply to Alice and bump. Okay, so let's just circuit draw output is equal to NPL, right? So if you look right now, the teleportation protocol is kind of complete. Okay, so now the thing is, I'm not going to run this on a chasm simulator. We need to get the state vector out, and as it turns out, I had some problems running the state vector simulator. So here I'm going to use something called as the air simulator. So air simulator is kind of a classical simulator, and it allows us to get the state vector. So I'm going to show you how to get the air simulator. It's kind of the same, it's kind of similar, not much different. The idea is the same. You have a backend, you give a job to the backend, and then you kind of get the state result out, right? So I'm going to have backend is equal to air dot get backend, right? So air simulator. So okay, this is one function which we have to use when we are using this. We are going to save the state simulator of the circuit. So this is the function which we use for that. Then we're going to have, let's say, our job is equal to okay. Instead of execute, we're using something called as backend.run. Okay, so we are having backend.run. What are we running? We are running the circuit. Okay, so okay, not this. We're just running the circuit. Okay, we have passed in the job. Now we get the result. Result will be job.result. Okay, and then what we do is we get the state vector out. So we have out state is equal to result dot get state vector. Okay, yeah. So print out state. You can check out the out state. Okay, did I forget something? Yeah, forgot something. And also we can have the same notes is equal to 3. We don't need a messy answer, right? So dot state, and then let's visualize it using something called as the block multivector. Okay, so I think I should have so from import not block multi-vector, and then okay, let me have this in a different cell, right? I'm gonna have this on the same cell. Okay. So, and then I'm gonna have plot block basically state. Okay, so let's see if I made any silly mistakes. Yes, I did. Run. Okay, no, not run. Run. Simulation failed. Okay, I got to run everything again. Okay, let's see. Okay, we have got the state vector out. So this does not make a lot of sense, but when we do this, you see, we had initialized the first qubit in this state, but now qubit 2 is in this state. Okay, just to show you a difference, I'm gonna also run this function here where we set this thing up, right? So I'm going to do p here. Here we had implemented this thing, right? So I'm going to do control C. We can use the same code. So if I run this now and I do this, you see initially when we were initializing this, qubit 0 was at this, because initially that's what we were at this state, right? But now after the protocol, okay, I messed up somewhere. Give me 1 second. I think there's something wrong. There's always something wrong. Come on, get the state vector. Yes, good. So we can ignore the first two qubits because it's in an entangled state, and when you get measurement, you can get kind of anything out. But you need to focus on the first and the third qubit. So if you remember, I told you, or Telemon told you basically, that the state in the first qubit will be transported to Bob in the, which was in the qubit 2, right? So this qubit to this, this qubit to this qubit. That is what we exactly did. We teleported this state to this state without applying an RX gate or without sending any qubits. We just sent classical variables. You can ignore this part basically because after measurement, we don't really care about those qubits anymore. So this was the teleportation protocol. And if you want to see, I can basically make the circuit on the circuit composer quickly. So we have the RX gate 5/8. Okay. Then, okay, we are applying the barrier for neatness. So double click on the barrier and you can just do this. You get this barrier out. Yeah. Then what we said is first we entangle Alice and Bob. So this is Alice and Bob. So I have entangled Alice and Bob. Now I'm applying a barrier again, right? You need to double click to get the straight line out. Then now we do something called as a bell measurement. This is the bell measurement. And then we basically kind of make this thing. Okay, now what we do is we measure these, measure these qubits out, right? We're going to measure these qubits out. And what we're going to do is we're going to apply a controlled Z and a controlled X gate. So how do we apply it? Okay, controlled X is kind of simple. I got this, but how do I apply controlled Z in a circuit composer? What you do is you basically drag this Z gate and you drag this dot here. So it's called a control gate modifier. You can just drag and drop it on the Z gate. What it gives you is 2 points now. What you can do is just join this, and now you have a control gate between the first qubit and the last qubit. Then we apply a CX gate here, and there we go. I told you the first state that we had, I guess. Where are you, RX? Yeah, 5/8. I promised you that this state is going to be teleported to that qubit in this way. Okay, so this is what we basically got. So that is the teleportation protocol.
Vishal?
We are, yes.
Sorry for interrupting, but we have only 30 minutes left. Okay.
No, it's done. It's done. I'm kind of almost done. Just 15 more minutes and that's it. Right.
Okay.
So thank you so much for letting me know about the time. So yeah, that's it about the teleportation part. So what you're basically doing is you're not magically teleporting some physical thing, right? You're teleporting information. So that is the best part about this. So now you might say, okay, why would you want to teleport information? Okay, isn't there a better way of doing this? Can't you just control C, control V? Turns out not. So in quantum mechanics, we have something called as the no cloning theorem. What basically happens is you cannot really have an identical copy of any other state, right? Because what happens is to make a copy, you need to look at the state. To look at the state, you're measuring the state. If you measure the state, you destroy the state, you collapse the state. Then what are you copying exactly, right? So like you lost the original thing. So in that case, in algorithms, in many algorithms, that's why you need to swap around qubit states, right? So this is kind of a good one of the tools you have to swap around gates. And entanglement is something because of which this happens. It's kind of very weird that you're having an entangled set of qubits and you just separate it out, and then one person just does something on it and gives you a classical result. It magically kind of affects the other qubit which you have in your hand, even though you are like really, really far away. So that's the weird correlation of entanglement, right? So where would you use this? The best part I would say is quantum cryptography. So Alice can basically shout out the classical outputs anywhere. And she can basically shout out and say, hey, I've got 0 and 1, and no one would get anything about what's happening, right? They'll be like, okay, someone's just shouting some random thing. But Bob will actually know what to do with it and how he can get the information out of it. So that's the best use, right? You can basically send some secret stuff and quantum data. So based on that, a lot of quantum cryptographic algorithms have been made, protocols have been made. You can check them out. There are a lot of robust protocols that have come out in the recent years, right? So that's something you can do your research on, right? So that's it from my side. I have so if we recap, we have done a few of the quantum gates, and we have looked at a few concepts, backends, and then we have looked at two mini games, right? Now let's here's a small let's say pathway which you can follow from this. If you've reached this point, thank you so much for listening, and it's super awesome that you have reached so long in this weekend. So thank you so much for coming in this weekend. And so while I don't believe anyone can basically dictate you what to say, we can basically advise you on where to go next, right? So here are a few tips from my side, because when I was learning quantum, I did not really have that much resources at my hand, and kind of like roaming around the dark here, right? So right now there is there are good pathways to follow. So why not uh, share a few about what could be great for you, right? So the reason why I say everyone to start with Qiskit is because Qiskit is kind of used around everywhere. So the good thing about this is, like, when you're learning Qiskit, and let's say you have a roadblock, there is a huge enough community that knows what Qiskit is and could probably help you out. And there are probably a lot of also resources on forums, and a lots of resources on, let's say, Stack Exchange, where people have come up with problems because there so many people have worked with it, and there's a chance that the roadblock you have might be have been solved by someone, and you can get the resolution out quickly. So that's why I would suggest for a beginners to keep your confidence high and keep your learning pace fast, right? So you can start off with the Qiskit textbook. So it's kind of a textbook which is beautifully divided into sections and subsections, starting from the starting basics of quantum mechanics, and like, not too much basics into quantum mechanics, but yes, you have a lot of explanations on based on what they are doing. So based on what operations they are doing, or what protocols they are following, or what algorithms they're giving, right? So I would suggest you to start from the Qiskit textbook. And let's say if you want to attend other events, you can start with events from Q-World. So you might have heard, I've seen a lot of familiar faces here. You might have come from Q Bronze or Q Silver or workshops like that. But if you have not, here's something that you can look into. So Q World is a non-profit organization that kind of runs workshops. And if you see the workshops and the materials, it's pretty comprehensive, and a lot of concepts are covered in. So you can go into that, and you can basically, it's like a 3 or 6 day event, and you can kind of, there will be live guided lectures like these, and a lot of notebooks and awesome resources there, which you can solve, and you can get a diploma, right? And it's kind of you get a nice boost when you get a diploma or a certificate, right? So yeah, I talked about the Qiskit textbook. Maybe I copied it 2 times. The next thing is, let's say you have more thirst. You want to quench your thirst. You want to look into other applications. You want to look into other applications or other implementations of quantum. The best I would suggest is you look at this particular playlist on YouTube, which is freely available on YouTube. It's a beautiful playlist. It's called the Qiskit Global Summer School 2020. So it covers a lot of topics in a short time. There are almost 25 or 27 videos, and there are like a few lab sessions there. So basically, there are like awesome instructors from IBM Quantum that are explaining each topics which they are good at, right? And it's like you have a theoretical walkthrough of the concept, and you have labs to work it out. But remember, those labs have code that is not really, I guess the code is a bit deprecated. It's kind of old, because at that time, I guess Qiskit was really in the starting stages, I guess version 0.13 or something. And Qiskit is growing really, really fast, and we are now at 0.27, which is like awesome. So just a heads up for that, but the theory part remains the same. Okay, so next is, do not be afraid to go into quantum challenges. The best part, personally, I have been pushed to be learning is after having a set deadline and a set amount of challenges there. So this challenge is like super awesome. You have like a set deadline of a week or like 2 weeks, and then you have a few notebooks which you have to complete. All notebooks have the prerequisite knowledge inside them, most of it at least, and you can basically read up on it and search terms from the notebooks and um, solve the challenges there. So here are the links of the previous challenges. So these previous challenges are pretty awesome. You'll find the answers of these in the same repositories, and you can kind of do it as a practice. And I would highly suggest you go and attend the next challenges. Do not be afraid. Do not think you're not ready. Just give it a go. What's the worst that could happen, right? And the next part is, yeah, it's very important to explore. This field is kind of awesome, and it's kind of, I would say, I wouldn't say exactly the newest kid on the block, because it has been there since like 1980s, but it started on 1980s. But the applications part is at least what everyone is exploring on. So the tools which you have, the quantum entanglement, quantum interference, and quantum superposition, is kind of a new paradigm of computing, right? So you can think in those ways and come up with new algorithms. And there are a lot of implementations that have not yet been covered and or have been researched into. So who knows, you might be the first one. The people in this call might be the first one to basically be in this workshop, to basically get some awesome algorithm, like let's say Shor's algorithm or Grover's algorithm, right? So that's also a possibility, and that's why this is so multidisciplinary. Anyone can get into this, right? So yeah, exploration also means you attend hackathons. Do not feel that you're not ready. You get in, form a team. If you're a beginner, form a team with beginners, work up on the challenge statement and try to get some result out. Because trust me, when you have such a time bound thing or some sprints, like one day sprints or 1 week sprints, it kind of accelerates your learning a lot. So here are a few hackathons that happen yearly. So you can look forward for these. Right now, I guess a few of these have already happened. You can wait for next year, or you can wait for new hackathons to come in the next winter, I guess, right? If you're into quantum machine learning, I would suggest you can look into Penny Lane's Xanadu. So these guys are kind of like leaders in QML right now. So you can leaders in the sense of at least material. So there's a lot of material for quantum machine learning on there. A lot of tutorials you can get started, have hybrid models, hybrid classical and quantum models too, right? And also Qiskit also has Qiskit machine learning right now, which you can check it out. There are also a lot of tutorials for that, so you can go ahead for that. Next, let's say you are not into the programming kind, you want to get into something else, right? You want to get into chip designing. So Qiskit also has something for that. So this is Qiskit Metal. Basically, it's a GUI based interface where you can design a superconducting quantum chip, the chip which IBM has in their backend, right? If you know the basic knowledge, you can kind of design it and get a fabrication model out. So this is a screenshot from one of the hackathons I had attended. This is like a certain architecture from a research paper, and then we can analyze it on ANSYS HFSS or and get some result out to see if what we have made kind of makes sense or not, right? And you can fabricate it if you want, right? So there's everything there for everyone. And yeah, you can also explore into some more advanced languages. So I believe that if you learn the basics of at least Qiskit, you should be able to also follow up the other languages. Of course, it's kind of like programming. If you know the basic idea of programming, you should be able to scale it up to other languages, bearing a few specific features of that language. So Circ is also one language I would suggest you can try out after you learn a bit, because this has a little bit of steep learning curve. But yes, this is a pretty awesome language. It is kind of focused towards making research, getting results out right now rather than waiting a few decades for better computers. So this is specifically tailored towards Niskera implementations. Then you have Microsoft's offering, Microsoft Q Sharp. If you are good at C Sharp, or if you're familiar with Microsoft's suite like .NET, this should be right at home. So it kind of follows a similar programming paradigm, and you can basically run it on their Azure Quantum Cloud or their simulators on your laptop right now. So the reason I do not suggest this much is because it's kind of like C Sharp, And I I personally feel that Python is kind of easier for people to start with, right? So you can start with C sharp, that's great too. But yeah, Python is kind of better to start off with. So you can check these links out. They have like an awesome, um, course that they have plotted out that explains everything out, right? Next is, let's say you want to get some formal education. This is something which I found was really awesome. So this is the Quantum Technologies and Computing Micro Masters from Purdue X. So you might say, okay, isn't it a crazy expensive university? If you are a student, you get a 90% discount here. So there's financial aid here, and you can get 90% out off here. Trust me, it's a really awesome course. I've personally been doing it. 4 of my courses are done out of 5. And unfortunately, I missed the very first course, which was the basic course. And now I have to do it in the winter part. Otherwise, I've done the other preceding courses. So I'm kind of going ulta. I'm kind of going reverse, right? So so this is something I would suggest. The instructor was super awesome, and you will be basically learning along with Purdue X students. Okay, so you are learning with the Purdue students. I was learning with we were in the classroom online with the other students, right? So that's one thing I would suggest. It's kind of a bit expensive, but you have a 90% discount if you are a student. You can, and if after the discount you can manage it, please go ahead for it. It's really awesome. Next is, if you want a little bit technically free alternative, it's not exactly free, but technically free, is courses from Coursera. So there are a few courses from a university called as St. Petersburg State University, which I kind of was my first contact for QC. And believe me, I started with the second course here, and I was kind of afraid of quantum computing after that, because it was kind of very straightforward, very, very mathematical, and I'm kind of a dum-dum in mathematical. So in mathematics, so it was kind of deterring for me. But then it was kind of a motivation for me to, why don't I understand this? I need to understand this. So kind of started to trace back and get prerequisites out, and then start to do this. So what the instructor did was, while I was learning it, I did not have this course. So the instructor realized after the feedback that there was a lot of prerequisite ready to be covered, so that needed to be covered. So he kind of made another course, which is an introductory course for that. You can get all these courses for free on Coursera. You just have to apply for financial aid. You start with quantum computing, less formulas, more understanding. You'll have like a good theoretical base on how to go about, and then you can start with this. You'll kind of understand a lot of things, call back from these. Then this is kind of a physics, kind of gives you a physical intuition of how quantum computing works. This is also a great course, but to realize these are uh, kind of a bit boring. The instructors do not, the first one is good because it was a new one, but these two were recorded a bit earlier, and kind of a bit boring. But trust me, it has very, very condensed information in there, right? So thank you so much for your time. That's it. We have come to the end of our workshop, and thank you so much for your time, for coming here for 3 days, listening to all our lectures. Lokesh, Shivani, and Bhavna, Uruj, Ansa, uh, and all the organizing team for basically organizing this awesome workshop. And yeah, if you have any questions, you can feel free to put it on Discord, or you can email me here, vishal.bajpayee@gmail.com. Well, that's it from my side today. Bhavna, you can take over. And thank you so much for coming on a Sunday and staying for, let's say, how long have we been talking? That's 2 and I guess 1 o'clock we started. That's 3 hours, 45 minutes. Thank you so much.
So
Thank you. Thank you, everyone. Continue, please.
continue.
So thank you all of you for joining us today for day 3. And I hope you all enjoyed this 3-day session and learned a lot of things about quantum computing. And thank you so much. If you guys have any doubt, then please ask or put it in the chat box. Thank
Yeah, we
you.
will be on Discord all the time, right? So do not worry about that. You have any doubts, you can post it there, right? And someone was asking for LinkedIn profiles. Trust me, I'm kind of clumsy there. I have not really made a LinkedIn profile properly. So if you see a profile that says Vishal and it's like progress profile in progress, that's probably me. But yeah, all the other profiles are there on the website, I guess. Ansa, can you just post the website link on Discord? All the profiles are there. You can just click and get the profiles of all the organizers, right? So thank you so much, everyone. Okay, and yeah, um, it was great having you guys here. Bye bye.
Bye everyone. I hope you had fun.
Bye everyone from my side too.
Bye, everyone. Take care. And thank you for joining us.
So I guess we can end it now. Everybody's done.
Yeah, we can
Yeah,
end it. Yes.
yeah, end it now.